Thank you very much for attending. Yeah, it's good to see a nice interest in finite element analysis. So this is the COMSOL team that decided to come. There's Alex, Taylor, and Joseph. Yes. So they have very interesting backgrounds: astrophysics, electromag, and quantum theory. What do you call today's workshop? We'll give an introduction to COMSOL, and then the titles that we see here. I think there may be a follow-up workshop at some stage, and we can maybe tune that a little bit more to the kind of the biochemistry, biomedical, or biological things that some people are interested in. Today's workshop is a little bit more on the physics side. Yeah. But I'll come on in. But anyway, thank you very much for coming, and I'll leave it to you guys.
Thanks very much, Patrick, and also thank you for helping me organise this. First of all, thanks for everyone for coming. It looks like there's a good amount of you here, so that's great to see. Yeah, like you said, I'm Alex. I'm the account manager here for Newcastle University here at COMSOL. I'm here with my two engineers, Joseph and Taylor. And yeah, as you see, the agenda is on the screen today. So in the morning, we're going to be focusing on electromagnetic stuff with an introduction to start. And then in the afternoon, it's going to be studies and solvers, and then application builders, digital twins, and surrogate models. So I thought I'd just like to start with a show of hands. So who actually uses COMSOL actively? Okay, I thought not as many as I thought. So hopefully that number will be a bit more after this session. But yeah, I'm going to start off with a quick introduction to COMSOL and what it is. So yeah, so COMSOL Multiphysics essentially does what it says on the tin. So it's optimized for multiphysics simulation. And one of the key benefits of COMSOL is that there's no limit to the amount of multiphysics couplings that you can have. And yeah, you can couple just about any type of physics together in one single model. It's not limited to just multiphysics, however, though, and lots of people do use it for single physics problems. This is largely due to the user-friendly interface and the ease of use, which I can demonstrate with the next slide. So here is the user interface of the software, and what you'll notice is that regardless of the physics that you're solving for, so here we've got the acoustic simulation of a loudspeaker. If you go to the next slide, here's a fluid flow over a sports car, and then we've got the thermal management of a battery pack. Very different physics being solved, but the underlying user interface remains almost exactly the same. So this makes it very easy to switch between physics and very easy to learn the software in general. So the main software is comprised of 3 elements. So if you move to the next slide. So the first one is the model builder. This is where you spend most of your time. This is where you set up your model, and you have all of the functionality for building the model, importing your geometry, building your materials, your physics, and your mesh. We've also got a graphical window and a settings tab for each of the nodes you can see here, and it's very easily laid out, very easy to use, and that's the main core of the package. But what we also have is the application builder. So this is particularly useful if you're working with people that may not be experts in simulation. You can create your model, and then you can basically create a simulation app, which just allows you to adjust a few key parameters, like you can see on the screen here, and you can very easily generate new results without being an expert in finite element simulation. Sorry. And then finally, we have the model manager. So this is our version control database, and this is essentially an organizational tool to help you keep track of your different models. A lot of the time people will have multiple different versions of the same model, so this is just a good way to keep track of which is which and not get lost in the different versions. You can organise it chronologically, alphabetically, or by physics, however you like. And yeah, and then here's the COMSOL product suite. So like I said, we've got COMSOL Multiphysics, which is the core package. We then have all of these add-on modules, which cover just about every area of physics and engineering. And yeah, so the first, well, now I'm going to pass over to Joseph, actually. He's going to take a deeper dive into the software, and he's going to start with a brief introduction into COMSOL and a live demo as well.
Yeah.
Cool, thanks.
Yes, so we'll start off with the user interface again, for those of you who don't know. Those of you who do know, you already know this. The main part of your model exists in this model builder window as a model tree. The model tree is constructed of nodes. You build your model in terms of nodes and their subnodes, which add different elements to the model. You have geometry nodes for adding geometry components. various physics nodes, you add boundary conditions as nodes, you add new equations essentially in terms of nodes. Every one of these nodes will have a right-click context-dependent menu from which you can add subnodes. You can also find all of your tools for adding nodes and adding elements to your simulation in the ribbon at the top. Every single node contains within it a settings panel. Within the settings panel, you've got settings for your node that allows you to control various aspects. So say you add in a definite temperature boundary condition, that's where you set the temperature, for example. It also contains an equations tab, which shows you what equations are being solved, what's being contributed to the overall model. One of the nice things about COMSOL is you have this graphics window, which is always there. So at the start of your model, you will tend to build a geometry. You can build this in COMSOL, you can import it from CAD, or whatever. There are various tools to help you do that. You'll end up with a geometry here. You add materials to the geometry by clicking in the geometry window. You add physics to the geometry, to the simulation, by clicking in the geometry window and selecting areas within domains and boundaries within the geometry window. When you have run your simulation and you're looking at outputs, they appear on the same geometry in the geometry window. So that's something quite nice about COMSOL. Probably the final thing we'll mention is there's an information window down here. And this just shows messages, sort of progress and log. As you're solving, the solver will give you various messages about how it's progressing. You can track your solution that way. So before we talk about physics, and before we end up in the next sessions talking about more specific aspects of COMSOL multiphysics, it's important to know about the philosophy. So COMSOL is built upon these pillars, the first one being user-friendliness. So I've already seen that the interface is the same for every physics interface. Every physics interface, no matter what you're solving or what you're studying, builds upon this node system. It's always constructed in the same sort of systems of nodes, same sort of idea of you add physics conditions, you add boundary conditions as nodes, you solve in the same place. And this makes it a lot easier for you to concentrate on a problem as you try and introduce new elements of physics, rather than fighting with a new user interface as well. We also have the application builder mode, which was spoken about briefly and we'll speak about in the last session of the day. Second point is flexibility. So engineers and physicists and scientists don't like black boxes. While COMSOL can be a bit of a black box if you want it to, generally the equations tab is always available to show. You can turn on this extra setting which allows you to see the more numerical side of things. The equations COMSOL is actually solving in the weak form. You can see lists of variables, you can see everything you want. Additionally, as you become an advanced user, you can start to play about with these. You can start to edit the way that things are applying. You can even begin to create your own, introduce your own general PDEs, general differential equations. You can solve your own equations. You can add boundary conditions. As you become more and more advanced, you may access the physics builder, which is something we're not going to talk about today. But the idea is that you can start off using COMSOL at a very sort of high level, just dragging and dropping nodes, which you understand based upon the equations in them. And as you get more and more comfortable, as needs must, you can start learning about how the numerical system actually works and start playing about with it there. So something else we need to mention about COMSOL is the sort of modeling that it is and why you're modeling. So in general, I'd say, being a physicist and coming from that background, there are two sorts of modeling software that you might use. The first is calculation software, and calculation software, I would say, is highly specific software that does a certain calculation to a very large accuracy and gives you a very large number of significant figures at the end. That is not what COMSOL is. COMSOL is simulation software. The idea being that it is quite general. You can do a very broad range of physics in it. It's not going to give you 10 decimal places of accuracy, but it is going to give you probably around 0.1% is probably sort of the numerical accuracy that you might expect. But the idea is not to get exact values. The idea is to gain insight about how your system is behaving and what you need to do with it. So the best model that you can make in COMSOL is the simplest model that captures the physics you're interested in. So for example, imagine you had a fluid flow problem and you had this pipe and it was imported geometry. On the outside of this pipe you had all of these engravings and all these various things. As long as they don't significantly compromise the structure of the pipe, there's no point including them in the simulation, because all you're doing is adding complexity for the computer to solve without gaining any insights. So the first step is always simulation. You will then always move on to model setup. You'll set up your model in COMSOL. You'll verify it. You'll have some examples, perhaps from a paper or from your own data, or just from how you know the physics should behave. And you'll check that that the model is representing that physics and replicating those results. If it isn't, you need to check your model setup. Okay? If it is, then you can move on to validation, and that's more to do with how your model meets the criteria of the model you were trying to create. From there, you can move on to the next steps of your process, whether that be optimizing your design or changing your design. And the idea being that simulation in this way, simulation rather than just pure calculation, it gives you improved knowledge about your device, your object, whatever it is you're studying. It can lead to better products because you understand, you can gain insight about what's going on in there. And it lets you prototype more rapidly. So instead of having to build a prototype, you can run a simulation, change various parameters in the simulation, and target prototyping. So this isn't just me saying this is what COMSOL can do. I'm going to give you a couple of examples of where COMSOL has been used to do this in the real world. So starting at the top, it was used to analyze the superconducting magnets in the Large Hadron Collider. All of these are user stories. They're all available on our website, written by the customer in question. So CERN produced this document for us and told us about how they used COMSOL to model the magnets in the Large Hadron Collider, how they model quenching in these superconducting magnets, how they simulated magnetic fields to help with their design, which probably saved them quite a lot of money, because if you do it wrong, it's a lot of effort to rebuild CERN. Next, we have sort of moving from research to sort of more heavy, I suppose what you might call heavy industry. A company called Hellenic Cables gave us a lovely user story about how they used COMSOL to design their offsea submarine cables to offshore wind farms. So cable modeling is it's another area where there's a lot that can go wrong, and if something goes wrong, it's very expensive to fix. So they tend to be very conservative with their designs. They tend to rely very heavily on industry standards and rules of thumb. Traditionally, it's very difficult to simulate these cables in full 3D. Recently, with various advances in the way that COMSOL was able to leverage symmetries in their operation, you can now, on normal computers, run these 3D models and gain insight from simulation. Hellenic Cables have done this in order to optimize their design and sort of move beyond the traditional constraints that the industry has imposed. Finally, I'll tell you a little bit about KitKats. Nestle used COMSOL to optimize their baking of wafers. So it's got, COMSOL is used everywhere, from the tip of high energy research through to very large scale industries, through to small sort of cost saving at scale that you will find in things like Nestle. So what I'm going to do now is we've sort of spoken a bit about what COMSOL is and why you might use it and how other people use it. I'm going to tell you a little bit about what COMSOL is under the hood. This isn't going to be a lecture on finite element analysis, primarily because I don't want to give it. But also, there's a huge amount available in literature if you are interested in how a finite element method works that I advise you to go look up. This isn't the place for it. This is just to give you a vague understanding of how COMSOL's applying it and how you can use COMSOL. So, at the core of COMSOL is what we call the multiphysics approach. And, it might be a bit surprised, given the name that COMSOL is COMSOL Multiphysics, but this is at the core of everything we do. So the idea being is that there are problems which you might want to solve which are electromagnetic in nature, or there are problems which are structural or are chemical or relate to heat transfer. And while these are all governed by sets of differential equations, the traditional way of approaching them is to approach them in isolation. So you would solve an electromagnetic problem, or you would solve a structural problem. The idea of COMSOL is that, sort of at the center of COMSOL, is that none of these problems really exist in isolation, especially in an engineering environment. you're always coupled between these different areas of physics. For example, you have an electrical device, there's a current flowing through an object that produces heat. If you have a very high current flowing through that object, that heat will deform that object. That heat will be conducted through the other objects. So you've got a heat transfer problem. You've got a structural mechanics problem. Imagine you have a chemical reaction. Your chemical reactants are dissolved in a fluid. They're flowing through a reactor. You've got a chemical reaction problem and you've got a fluid dynamics problem. Perhaps that's an exothermic reaction. You've also got a heat transfer problem. As you're looking for how, if it's a very exothermic reaction, how that affects the local environment and the pipe you've got through it. You may want to add your own equations. You may be doing something a little bit more unusual that perhaps COMSOL doesn't have a feature for yet. You can add your own with equations. You can couple them to the existing electromagnetics. You can do things like optimization. You can optimize your design for specific values of, say, a magnetic field. You can optimize coils to approach a certain magnetic field design shape and magnetic field strength. All of these you can do in COMSOL because they all can be linked together, sort of from the outset. This was intended from the beginning. They aren't separate products which are all being sort of pulled together. It is one product with different aspects. From these multiphysics designs, you can move to applications. We've already spoken about the application builder, the idea being that I think we call it the democratization of simulation. There are a large number of design engineers who don't need to know, it's not necessary for them to be an expert in, sort of say, building models, even with COMSOL, but they need to be able to see how their design changes will affect the final results. You can build these apps with restricted inputs and outputs that you can distribute to your engineers. You could distribute it to students and use it as a learning experience. There are people who do, I believe. They have this large repository of apps that they use for teaching, for example. You generate outputs, you can generate reports all from multiphysics. So this rests on the way that physics is sort of done in COMSOL. So we split things up into these things called physics interfaces. So there are multiple physics interfaces within a given module. So you might have seen the previous slide, we had this big product suite slide, which we showed you, here's COMSOL, here are all the add-on modules. Within the add-on modules, there will be multiple physics interfaces which all relate to each other. So you're going to see examples later of a few of these modules, and we'll take you through the physics interfaces that are there, things like the AC/DC module and the RF module. But the general principle is the same for all of them. All of these interfaces, they describe a sort of small and highly related subset of physical phenomena which are generally governed by the same sort of equations. So, for example, you may pick a module in AC/DC, and at the center of that module is a set or a subset of Maxwell's equations. Within every physics interface implements those equations into the simulation, depending on how you assign it. And from there, you can add related boundary conditions. So say you were in a heat transfer problem, you would gain access to boundary conditions like fixed temperatures and external heat fluxes. In this solid mechanics example, so solid mechanics here would be the name of the interface, you get this linear elastic material automatically. You could change that, you can add non-elastic materials if you have the appropriate modules and things like that. And then you get boundary conditions. You get things like a fixed constraint which fixes one side. You can have boundary loads, which are forces applied from the outside onto your system. You can have rollers, you can have internal systems. And all of these add something new to the system of equation COMSOL is solving. COMSOL is quite nice in that it tends to give you these equations in the equation viewer in a form that is best for you to understand. Obviously, a numerical system isn't sitting down and solving a set of differential equations in the way that you would expect it, but we can relate them to those, and that's what COMSOL tends to show you. So, once you've added a physics interface, you can add other physics interfaces, and this is how the multiphysics coupling starts to build together. So once you've added, say, electric currents, and you're starting to model your electric currents, and you've set up your boundary conditions, you can add heat transfer. And you'll have a different set of boundary conditions there, and you will add a multiphysics coupling between them, many of which are built in. You can also define your own with your global equations, etc. As I said, which modules you have on a COMSOL license determines which physics interfaces are available to you. And so that's why these modules are sort of lumped together in lump together similar sorts of physics. So I mentioned that we apply physics. What do I mean by that? So if you remember in one of the previous slides, I showed you the geometry window. And I said that you'll build a geometry in COMSOL. That is essential, whether you're in 2D, whether you're in 3D, you build some sort of geometry that represents your problem. And you can do that either with the inbuilt tools that COMSOL has. It has a large number of tools built in terms of primitive shapes. You then use certain operations upon that to change the shapes and to extend the shapes, etc. You can take 2D planes and extrude them into 3D. You can take 3D structures and collapse them into a 2D representation. You can also import from CAD software. And there are various tools available in COMSOL which allow you to repair this CAD import if there are small features that appear in the import process, small imperfections. You can fix edges back together and things like that. The whole idea being is that you end up with this geometry to which you can assign properties. So the geometry is generally, this is the 3D representation. You have domains, which are the large volume spaces. Boundaries are the surfaces between domains or on the edges, on the outside, sorry. Edges are the lines between boundaries, and points are points. When you move to 2D, this naming changes slightly because the idea of an edge disappears and a boundary is an edge. So a domain is always the same dimensionality as the problem you're solving. So essentially what you do in COMSOL is you will have your geometry and you will assign physics to different areas. So an example being, let's take electric currents. You may have a wire in an insulating material. You can assume to whatever sort of tolerance you like, whatever sort of tolerance is appropriate, that the current in that insulating material is 0. You don't need to solve the electric currents interface in that insulating material. It's going to give you numerically 0 when you know that it's 0. So you can save computational power by only solving in the wire. To do this, you'd only select the elements of the geometry that relate to the wire. This is also where you'd select how you apply boundary conditions. Say at one end of the wire, you'd have a surface boundary, cutting off that thin cylindrical domain. That's where you might apply your terminal condition, which specifies, say, a voltage. It may be where you apply your ground condition, for example. So I said I'm not going to give a lecture on the methods by which COMSOL works, and that's true, but just to give you a quick idea, in case you're interested. Of course, when we have a differential equation, a partial differential equation, whatever you like, the idea is that you have here in one dimension, you have boundary conditions at either end, say u equals 0, and we know what u looks like, where u is the solution to the equation, I should mention. And we know what u looks like at some value of xl, and then between 0 and L, we have a continuous solution, which varies depending on the differential equation. Of course, this isn't a natural thing for a computer to think about. Computers don't deal well with these concepts of continuous solutions. So what we do is we end up discretizing the space. And this is the concept of the finite element method, is you break up your space. Here it's a 1D line. You can sort of imagine how this would extend to 2D and 3D. You break up your space into finite elements. You break it up into finite little sets bounded by nodes. The solution is then calculated at each node. Okay? And then from that you can interpolate based on sort of this system of basis functions which you can apply at the nodes. So in your algebra you interpolate the solution between them. The idea this is called meshing, and it's something that we're not going to go too deep in, but is always something that will be there in your COMSOL models. So the idea being essentially the core concept of meshing being a coarser mesh will generally solve faster than a finer mesh, and a finer mesh will be more accurate. The coarser mesh having fewer nodes in a given space, and therefore representing the underlying geometry less well, and the finer mesh will have more, but then leading to higher computational, leading it to be more computationally intensive. There are a couple of caveats to this. One caveat being is that if you make your mesh too coarse, sometimes the solution won't converge as you actually start missing elements of your geometry, and you end up missing things out. So ultimately what COMSOL is doing is it's taking your sets of differential equations, in what we call the weak form, and it's expressing them into a form that a computer is very good at understanding and very good at solving, this sort of linear algebra form, where it sort of builds your model up in terms of a stiffness matrix and a load. Those words come from structural mechanics, of course, but they're used for everything. And your solution is then this vector over this 3D basis, which discretizes your geometry. The computer can solve that. Computers are very good at solving linear algebra problems. The key part is that it has to invert this stiffness matrix, and that is often where most of the computational effort that COMSOL is putting in goes. This is a sort of a representation of a stiffness matrix. Essentially, the colors give magnitude. It's just sort of a color map representation. And luckily, when you use the finite element method, quite often your matrices are sparse, which makes life a little bit easier for solving. So that's just sort of the idea. As I said, it's probably best if you're really interested in exactly how the finite element method works to go and sort of look it up yourself. It's very well documented. But for those of you who are just interested in using COMSOL, it's enough to know that this is why your mesh is, and this is why the properties of your mesh are what they are. So the general workflow we have when building a COMSOL model is you'll start off with a geometry. You'll always begin with some sort of geometry. There are exceptions. You can import a mesh and then build a geometry from that, where you import the mesh as an STL file from say a 3D scan. But generally, you start off with your geometry. You assign materials to these geometries. These give certain areas of the simulation properties. So, for example, use electric currents again. You'll see why I keep going back to electric currents in a minute. Use electric currents again. You may assign a copper material to various wires, and that will have associated with it a conductivity and a relative permeability and relative permittivity in all this, so that COMSOL can access relative permeability, say, material properties associated with domains and boundaries, edges and points. You then move on, you apply your physics in the areas to which they're relevant. So as I said, imagine you had a wire coming through there. You might only want to solve electric currents in the conducting elements. You'll ignore the insulating elements. So you would only select the conducting elements. You want to save yourself all this sort of numerical trouble of solving in an insulator. There's something more to that as well. It's not just saving yourself time. Remembering that a computer is a computer and it's only got so much accuracy in it. If you imagine that you're solving for electric current flow in copper, which has a conductivity on the order of 10 to the 7 Siemens per meter, and then you also solve in some very good insulator, which is very close to 0, you have a massive range of material properties there, and a massive range of scale there, and you end up getting to the situation where you might be trying to do big number minus big number equals small number, which is a very dangerous thing to do with computers. But yes, so you assign materials, you assign physics to your geometry, you will then mesh your geometry, which produces a representation of the geometry that COMSOL can understand and the solver can understand. When you first start out, you can leave COMSOL to do this for you. It has a variety of inbuilt meshing tools and will automatically mesh geometry according to the physics that you put in as to what it thinks will be best. You can tweak this, and when you start becoming very sort of more advanced and you start doing more complex models, you might be interested in meshing yourself to optimize for time, say, or for the accuracy in a given location that you're particularly interested in. You then move on to this step we call the study. This is where you define. This is where your solver hides. Generally, COMSOL does what it can to make itself as not intimidating as possible. So, as it will automatically mesh for you, it will also automatically pick solver properties that it thinks is best. You can always go in and modify these. It's actually quite simple to get to them. I will leave a discussion for the solvers for the Studies on Solver session, however, later. In general, you get things like, you get a choice of things like a stationary time-dependent frequency domain. This is it's sort of, well, I suppose you call it the regime in which you're trying to solve your differential equations. So if you were interested in transient properties of your differential equations and their time-explicit behavior, you'd solve a time-dependent study, which will give you that. It'll give you the solution at various time steps, and you'll be able to see how the solution evolves. If you're only interested in the steady-state solution, you may want to take the stationary study step, which will only give you the stationary solution, the steady state, after transients have decayed. You may be interested in frequency domains. Since we're going to be talking about electromagnetic modelling, this comes up quite a lot, where sort of this harmonic dependence on time has been assumed in the model, and you're being given these sort of these phasor magnitudes as your outputs and things like that. Finally, you'll get the results. As I said, all these plots that you can get will, by default, be on the same geometry that you've been modelling in. You can always do sort of cuts in it and get 2D geometries out of a 3D geometry, for example, or you can extrude, say if you're doing a axisymmetric study, a 2D geometry into a 3D geometry. But in general, it will be on the same geometry you've been working with the entire time. And you can do things like color maps, you can do surface plots, streamlines, arrows showing vector quantities, etc., etc. And then I guess from the modeling workflow point of view, once you've done this, you'll go back to the geometry and you'll start adjusting your model, unless it's perfect. And it's exactly what you were after. Something else that we do need to go through, this introduction sort of is going to end here, and I'm going to move on to a live model, because I want to spend a little bit more time on the live build, because I tend to feel COMSOL, being a computer program, it's a little bit easier to talk about and explain how things working actually in the computer program. But there's some things we need to talk about in terms of the general naming conventions which I might use, and I don't want anyone to not follow along. So interface, I've explained, this is the physics interface. This is where your sets of equations live. It's where you it sort of determines what boundary conditions you can add, things like that. You can set them up in terms of the nodes, or you can manually write equations. You can even, if you really wanted to, write a COMSOL model in terms of Java code. I don't know many people who do that. So there's this other naming convention, single physics. That's a model with one physics interface. And multiphysics is a model with more than one physics interface. Quite straightforward there. We then have this idea of coupling in multiphysics models. This idea that you have your two physics interface, but there's got to be some sort of connection between them for there to really be much point in having the two. You can have one-way coupling or two-way coupling. So in one-way coupling, the formulation of one physics interface depends on another, but the reverse is not true. So an example that we're going to use in a bit would be something like, imagine if, well, we won't use this one a bit, I'll use a different one. Imagine if you had a chemical reaction where the reagents are dissolved in some fluid, but don't make up a significant fraction of the fluid. Okay, they don't make up a significant fraction in terms of mass. They don't affect the fluid flow in any way. The fluid flow physics will determine at some level the chemistry that's going on, because it will determine how concentrations mix. But the relative concentrations in the chemical reaction physics will not affect the fluid flow physics, because they're not present in large enough quantity. Say you suddenly make that reaction highly exothermic, and you add in a heat transfer sort of element, and then the fluid has heat temperature dependent properties. Then suddenly you've got this sort of set of couplings where you're essentially coupled two-way, but from the fluid flow to the chemical reaction, which then determines via this heat transfer the properties of the fluid flow itself. You'll see this word nonlinear come up a lot. This is just, essentially, it's the property when the model's solution is not directly proportional to the input. So generally electromagnetics is linear physics, however you do get all these nonlinear magnetic materials which will make the problem nonlinear. Nonlinear problems are generally harder to solve, and they generally take longer to solve as well. And you do need to be a little bit careful with them when you're sitting down and solving them. And finally, I've spoken about the mesh. It's the division of the geometry into these finite elements that the finite element method can use to run your simulation, to solve your sets of equations. Generally, these are of a very simple shape. So in 3D, you'll mostly see tetrahedrons. You may see some hexahedrons, depending on how you've set up and what's ideal. In 2D, you'll mainly see triangles. You may see squares. it's a good idea usually to keep the number of sides of your elements as few as possible, because that reduces the number of nodes which are being solved for, and it generally reduces the size of the mesh and the number of degrees of freedom in your model. However, sometimes it is necessary to have these more unusual shapes. An example of that is in semiconductor physics, where there can be very rapid changes in carrier concentration across a very small space. It's very good to have a highly structured mesh there, where you can really define smaller mesh elements in an area so you can resolve these changes. And they're sort of in 2D, a quadrilateral mesh is quite easy to do that with. You can just map the mesh across regular shapes, usually. So we're going to move on to a live demonstration now. And this is on something called the resistor beam. And it's one of our favorite live demonstrations. If you've ever done the intensive course that COMSOL offers, it's something you'll have seen before, so I apologize there. If you haven't done the intensive course and you want to do it again, then if you want to do it, then I'm sorry, this is a spoiler, but we're going to do it. So the idea is that this is a small example which shows you a couple of multiphysics between electric currents. It shows heat transfer, and it shows structural mechanics, which is one of the reasons why it's our favorite. It's a very sort of simple system to get your head around as well, which is an advantage. It also shows an example of CAD imported geometry in a COMSOL model. So the idea being is you've got this, you imagine you've got some sort of circuit in a circuit board, all made out of copper, and you have this element of the circuit board, which we call the resistor beam, which is attached to the circuit by a solder. The circuit itself is copper, and this is some circuit board material. And the idea is that you have current flowing through the circuit. As it flows through the resistor beam, you have resistive heating in this beam. Because you have resistive heating in this beam, you have temperature changes and you have structural changes that result from these higher temperatures. It's a small segment of a larger circuit, and there's an idea of showing simplification. Say the rest of the circuit is not of much interest to us when we're trying to look at the structural deformation of the resistor beam. There's no point modeling stuff that is irrelevant, because we can use boundary conditions to sort of, as if they were there. So as I said, the idea here is that we have current flowing through the circuit. We'll model this by setting a voltage across this element of the circuit of it'll be 0.1 volts. COMSOL will solve for the current in the conducting elements. You'll then move on to this multiphysics coupling of Joule heating, which will allow you to get a heat source due to this current into the heat transfer part. The copper is encased in this circuit board material, and we're going to model conductive cooling in the circuit board from the copper. We're going to sort of ignore air in general on the principle that it's not very thermally conductive and it's not very electrically conductive. We're going to consider just that it's in dry air. And then you have this thermal expansion multiphysics coupling, which couples the thermal analysis, it couples the heat transfer interface to the structural mechanics part of the interface, which allows you to see the thermal expansion due to this change in temperature. So the objective is to find, given a specific applied voltage, what's the deformation and stresses that appear in this resistor beam. So I'll tell you a little bit about the Joule heating as an example of a multiphysics coupling. So we have two physics interfaces. One is electric currents. This solves for the electric potential. One is the heat transfer in solids. This solves for the temperature. In this case, the electric potential and the temperature are they're the dependent variables of each interface. They are what is solved for. So when COMSOL sit down and solve, it will only solve for these dependent variables, and everything else can be produced from these dependent variables in post-processing. So the multiphysics coupling here, Joule heating, which you can find under various multiphysics tables, tabs, menus, will couple the heat transfer and electric currents interface sort of by adding, you can think about it as adding these terms into the equation. So if you think about one-way coupling, you'll add this electromagnetic losses term into the conservation of energy, which is the governing equation of the heat transfer interface, which adds this electromagnetic heat source essentially into it. That would be one way. If you were going to do it two-way, you may think about, say, that the conductivity of the copper were temperature dependent. That would make it a two-way coupling, and suddenly the electric current is dependent on the temperature, and the temperature is dependent on the electric current, which is from the electric potential. We're not actually going to show you the two-way coupling because it doesn't qualitatively change the results in this example, and it's really a little bit underwhelming to show in this example. There are examples which show very good two-way coupling, however, all available on the COMSOL website. So whenever we think about building a model in COMSOL, it's good to sit down and think about what physics interfaces we're going to add and why we're going to add the different boundary conditions that we're thinking about. So if we think about the electric currents interface, we're going to need a ground somewhere, and we're going to define a positive electric potential at this end of the circuit. The idea being that through the circuit there is a total potential difference, or a voltage across the circuit, of 0.1 volts. As I said, we're going to assume that the air is just dry, and so completely completely insulating. And actually, we're going to assume that the circuit board itself is completely insulating. So we're going to have boundary conditions on all of these, apart from here and the bottom, of just electric insulation. And this will solve for the current. Pardon me. In the heat transfer interface, suddenly we do want to include the circuit board, because the circuit board has a more relevant thermal conductivity and is in fact providing some of the cooling, well, all the cooling that the heating copper is experiencing. Again, ignoring the air, but we're going to assume that there is some circuit boards out here somewhere. And how are we going to model that? Well, what we're going to say is we're going to assume that that is all at a fixed temperature. You've got this sort of external thermal bath that you're coupling your objects to. So you can fix the temperatures on these external boundaries, which would be connected to the rest of the circuit board. Finally, we have the solid mechanics. Again, we need to think about boundary conditions. We're going to model everything as a linear, elastic material, and that will be good enough for this. We need to think about the boundary conditions. So if you think about the fact that there's the rest of this circuit board existing, and there might be stuff under it as well, the bottom is going to be given a fixed constraint. So the bottom is going to be held in place. Incidentally, the solid mechanics interface is solving for its dependent variables, the displacement for a displacement vector. So this will be held in place and displacement will be 0 along the bottom. On the sides, there's a similar sort of boundary condition we need to apply, because if you think about it, there's all the rest of this circuit board around. It can't expand into that circuit board. That's being held at, say, a constant temperature. It's existing as just this external boundary condition pressing in on the resistor beam itself. However, along the top, you only have air. And we really don't need to consider, in this simplification, we don't need to consider anything like the pressure of air upon the top. So it can deform along the top, and that means at these edges it can deform parallel to this boundary, but not perpendicular to this boundary. So we're going to use a condition called roller, which will allow that. So let's now hop into COMSOL. I'm going to have to sit down for this, I'm sorry. I can still see you all though. So if you've never used COMSOL before, welcome to COMSOL. If you have used COMSOL before, welcome back. Oh, you can't see it. This isn't good. There we are, that's better. Right, if you have used COMSOL before, welcome to COMSOL. This is probably the screen which you'll be faced with when you first open up COMSOL. This build a new model. You'll have the choice between Model Wizard and Blank Model. Generally, Model Wizard is the way to go. So this will sort of guide you through the process of setting up the bones of a model. So in this case, so the first step is to choose your space dimensions. So is your model a 3D model? Is it a 2D model? 2D axisymmetric? You have various 1D choices as well, which are available for more sort of specialized physics interfaces. An example would be in the semiconductor model. you have an interface for solving the 1D Schrödinger equation. That would use a 1D study for it. So in our case, we've got a 3D study. I'll move out of the way. So we're going to choose 3D. We're then faced with this option to select physics. Now, we could go through and add physics interfaces individually, so we'd be interested in the electric currents interface, say, and heat transfer in solids. But if we come down to structural mechanics, we can see beyond just these regular interfaces, we also have these multiphysics couplings already set up. So if we click thermal structure interaction, we see we have an option here for Joule heating and thermal expansion. If we double click this, or you can use the add button, to add these physics interfaces to our model, you'll see we'll get the solid mechanics, heat transfer in solids, and electric currents interface, and we'll get the relevant multiphysics couplings already added in, so thermal expansion and electromagnetic heating. So as I mentioned, the interfaces will solve for a small set of dependent variables from which all your other quantities can be got out in post-processing. You can change what they're called here if you so wish. So for example, if you didn't want electric potential to be V, you could change it there, if that's sort of what you're used to. So we then move on to the study. In this case, we're going to select a stationary study. You have your general study types at the top and various preset study types that are available for certain physics interfaces that you've selected. Until you start doing more specific sorts of models, you're going to be probably using the general studies. We're going to be using a stationary study, in this case, already interested in the steady state result. Double click that, we give it a moment, and COMSOL will have added all these things already to the model builder. You see we've already got these physics interfaces available, and we've already got the multiphysics couplings, and we've got a 3D geometry. So if I wanted to build this out of primitives, I could add a block, say, and I would do various operations, add more primitives to construct that. However, I'm not going to do that. What I am going to do is I'm going to import a pre-existing geometry. So if I go to Browse, I'm going to choose resistorbeam.mphbin. mphbin is sort of COMSOL's native geometry file format, just so you know. You can import geometries from other models as well. You can import them either by exporting them from that model as mphbin, or you can import them as a sequence from that model, and you'll have access to the full geometry sequence there. So if I import this, let's just build it to make sure. There we are. We get the same geometry that we expected from the slides into COMSOL. Something that's worth mentioning is that you have this graphics window. You can control and move about this graphics window. You can rotate it if you hold right mouse. You can shift it if you hold left mouse. Middle mouse button to zoom in and out. You can hold, say, Z, and it will rotate about the Z axis, etc., etc. It's just useful stuff to know. And if you haven't done the advanced course, it's the sort of stuff where you can have been using COMSOL for a long time and not known it's there. So just in case anyone didn't know it's there, there we are. So we've started off, we built our geometry. The next step in the usual modeling procedure is to add our materials. So you can see all of these domains are lacking materials and are lacking material properties. So if we right-click on materials, we can also do this through the ribbon. I tend to like the right-click context-dependent menus. We can have the choice to add things like blank materials, where we can define our own materials, or we can add from the pre-existing material library of COMSOL. This is quite a useful part of the COMSOL software. It has all these built-in material properties. So if I add copper, for example, you'll see it already has electrical conductivity, coefficients of thermal expansion, etc., and a variety of other properties which aren't used. It's worth remembering, though, that this is not exhaustive and it is not authoritative. Okay, if you are producing your own model and you're trying to match something from a paper, and the sort of the literature value is slightly different from the value we have in materials library, use the value from the literature. Possibly tell us, because of course we just have to we try and keep this up to date. Yeah, it shouldn't be taken as authoritative, and it's certainly not exhaustive. It's just useful, especially when you're in the early stages of building models. You're also able to, you can also add this and edit them. So I could change, say, any of these values that I wanted to whatever, to correct them for my model, if that was so needed. So we'll see copper is automatically applied to all of the domains. That's not right, but it's so that if you have a very complex model, you're not going to have to go through making sure all these very small domains have a material. You're not going to end up accidentally not assigning material. There will be some material. Usually you might have an air box and you define air first, so that if you missed any material properties, you'd have air there. That's just a quality of life thing. But say we add circuit board, it doesn't get applied to anything. We only want it to be applied to domain 2, which is the circuit board. We select this in the geometry window. We go back to copper and we see it's overwritten the copper assignment. The order in which your materials appear in this tree matters. Okay, so say that I'm also going to add now the solder. Say I were to select this domain again by mistake, you'll see it will overwrite the circuit board and the copper. But if I move the circuit board below, it's the circuit board that gets applied. The order matters. So all I'm after now is to add solder to the little connections between the resistor beam and the rest of the circuit. Sometimes you'll find it difficult to select. You can zoom in, or if you hold your mouse over this domain and you use the scroll wheel, it will scroll to adjacent domains or adjacent boundaries so you can select them easily. So, and this is, as I said, the material library is not exhaustive and it is not authoritative. As we can see, solder is missing a relative permittivity, so we're just going to add one in there. Because relative permittivity is demanded by the electric currents. If you see this little stop icon, it means there's a problem. If you see a little warning sign, it means it'll run, but it's something to be aware of. So if we right-click on here, we can go to the requesting node and see what's requesting that property if we're not expecting it to be required. So on the topic of electric currents, we'll start off here, since that's the first one I explained, and add our physics, add our boundary conditions. So the first thing we want to do is we want to completely deselect domain 2. Because it's our circuit board, we're going to say for all intents and purposes, it's a perfect insulator. We're not going to bother trying to solve the electric currents interface in here. It'll only cause us problems. So now we're only solving the electric currents in the conductor parts, the copper and the solder. You can see ultimately it's solving this set of equations. We'll talk a little bit more about what it's actually doing in the low frequency modeling part of the day. But you can always see these equations, and if you had multiple studies, you could see the different sets of equations that are being solved in each study. You'll automatically get this set of loads like current conservation, which applies these governing equations. You'll get electric insulation, which is the default boundary condition, which will appear around everything selected in the electric currents. In this case, it's the boundary we want over most of these external boundaries. And we get this initial value node, which isn't important for us now. What this initial value is, it's an initial value for time-dependent studies, or it's an initial guess for nonlinear problems. It's not really relevant in this case, so we can ignore it. But you'll always get this initial values node in here. So we want to start adding the other boundary conditions. We want to add a ground, and we want to add a well-defined potential. If we right-click, we get this window again. We can add a ground boundary condition. We turn this over, and we select these bottom panels. And then this time I'm going to use the ribbon just to show you. We've got electric current selected, so we'll have domain boundary pair edge conditions which are relevant to the electric currents, and we're going to add a terminal. We're going to make it a voltage excitation. So if you look at the equation, all it's doing is setting the electric potential to this specific value at this edge. I could put 0.1 volts here, but what I'm going to do is, just for those of you who don't know and would find it convenient, COMSOL keeps track of units. There are exceptions to this. It doesn't keep track of units to non-integer powers. It won't stop your simulation if you have units of non-integer powers. It'll just warn you that it hasn't kept track of the units. But in this example, say I can put in 100 millivolts and it has a value of 0.1 volts. It keeps track of these sorts of conversions for you. You add units with these square brackets. And that's actually everything we need to do in the electric currents part. So we'll close that just, to make things nice to look at. Into heat transfer, again, we have all of these default nodes. We've got a solid, we've got initial values. Thermal insulation, in this case, is the automatic boundary condition that's applied. But we wanted a well-defined temperature on all of the non-free boundaries. So what we're going to do is we're going to add this temperature boundary node. We're going to leave it at 293.15 Kelvin, which is just the default room temperature. It's also the default reference temperature in that model, which is convenient. And instead of just trying to select all these boundaries individually, if I right-click here, I can go to Group by Continuous Tangent, and I'm able to select all of these planes which are next to each other. Oh, I selected the wrong one. You can just deselect it. Pretty sure I deselected that. Yeah, so everything where it's in contact with the rest of the circuit board, we've added a well-defined temperature boundary condition there. Okay, now we're into solid mechanics. Again, we have our basic linear elastic material. If you have the various solid mechanics module, or the structural mechanics module, sorry, you will have access to different sorts of material models. Here we're just going to use linear elastic material. That's all we really need. We're going to add a fixed constraint, which, as I said, if we look at the equation, just sets the displacement vector as 0, and it means that the bottom won't move. And we're going to use the roller boundary condition on the sides. This just means that it can't move normally to the planes in which we select. It can move tangentially, which allows it to be free at these top edges. So if we go around and select all of these, there we are. And at any time I want, I can right-click and deselect Group by Continuous Tangent, and then I'm back to selecting individual boundaries or domains, etc. So that's actually all the physics interfaces set up as I spoke about in the slides. We have these multiphysics interfaces which have been added automatically because of how we set up the model in the model builder. So we have thermal expansion, which is present on all of the domains because all of the domains are present in both the structural mechanics and heat transfer interfaces. It couples the heat transfer and the solid mechanics just by adding this extra temperature-dependent term into the linear elastic materials set of equations. Electromagnetic heating is a little bit different because the circuit board domain is not included in electric currents. It's also not included in this multiphysics interface. And this couples electric currents to heat transfer in solids as we discussed in the slides. Imagine you hadn't set up this multiphysics coupling in your model builder and you wanted to add it. Well, then you can either by right-clicking here or by using in the physics. We'll go to the Add Multiphysics, and you'll see all of the inbuilt multiphysics couplings that are relevant to the selected interfaces you have. So say I wanted to just couple electric currents and heat transfer. These are the multiphysics couplings that are available. If I just wanted to couple electric currents and solid mechanics, you see I could also add piezoresistive and piezoelectric materials in here because they would couple solid mechanics to electric currents. I'm not interested in doing any of that, but that's where you'd find it. The final thing we'll mention is the mesh. So if we build the mesh, this is the physics-controlled mesh. As you can see, that you've got the default option is that COMSOL will pick a mesh for you. This isn't a particularly difficult model. There's no reason to sort of try and really refine the mesh too much. You can choose from preset element sizes. So say I wanted very coarse mesh elements. It would be coarse, and we get this information node saying that there's a face whose size is smaller than the minimum element size set by coarse. So you might look at that and go, oh, maybe I need a finer mesh. So if we set it to fine and build, that information node goes away. But we see that when it was at normal, we had 6,000 domain elements. At coarse, we have 2,000. And at fine, we have about 9,500. And that will impact the number of degrees of freedom that the system's solving for. So finally, we go into the study step. We're going to leave generate default plots on, just because if we wanted to look at the solver beforehand, in fact, no, let's just solve it. You can see it's going to be solving for all these physics interfaces. We'll click compute. COMSOL won't let you do much regarding the model while it's computing. You'll get a progress bar. there. This is pretty quick, so it's difficult to show you the progress panel, but you get a log telling you any information. This is quite a simple model. You get convergence plots. This is the convergence for the electric currents part, solid mechanics part, and temperature. It's solved quickly in 2 segregated iterations. Here is the convergence for each iteration. Sometimes, if your solver is taking a very long time, it may be worth looking at these convergence plots, which often appear, especially for iterative solvers, and you may find that this line has leveled out around here, which indicates that it's not going to converge to the tolerance set in the solver, which is by default 10 to the minus 3 error here. So let's go down to the results tab, which has appeared because we now have a data set which is pointing to the results of study 1, and we have these plots which have been automatically generated. So if we look at the plot of the electric potential, it's given us a volume plot of just the electric potential, which is one of the key dependent variables being solved by the electric currents interface. And you can see we start at 0.1 here, and it varies throughout the resistor beam down to 0 here, well, numerically 0 here. Remember, this is, as it's a constraint that's being added in COMSOL, it's sort of constraining it to be numerically 0. There are certain things which are constrained to be exactly 0 by the way the equations are set up. So, for example, in the electric current, it is assumed there are no magnetic fields. So B is 0 exactly. But you've set an extra constraint in the model of the electric potential is 0 on this boundary, and that's numerically 0, which in this case is down at 10 to the minus 22 volts, which is 0 for all intents and purposes, really. So we can see that varying. So from the electric potential, we can get the electric field, and we can plot the electric field. So if we look, this case, it's a multi-slice because it's showing it wants to show us inside rather than sort of the surface. And you can see it starts off as sort of constant. You have a nicely varying electric potential there. We have material discontinuities here, and we have structure becomes very thin here, and you have a rapid variation of the electric potential here, which, interestingly enough, is going to relate to a higher temperature there, which is then coming from, this is the multiphysics part coming in. That temperature is because we've added the Joule heating interface in. If we didn't add that in, we wouldn't get a result like this. For the temperature, sometimes we don't want to have sort of something like a volume plot here, as this is just this opaque 3D plot. We can't really see what's going on inside. You may want to do something like, let's add isosurface for the temperature in Kelvin. Let's change it to degrees C. Hopefully this will work. We'll plot that, and we will disable that. And yeah, so you have access to these now, sort of like, this is the 3D equivalent of a contour plot, essentially. So if we change that from rainbow to something that looks a little bit more temperature related, let's go for heat camera. And maybe it looks a bit nicer if we increase the levels. Little plots. You can see sort of how the temperature is varying within the object as well as just on the outside, and you can still see that we get the highest temperatures in the resistor beam. Again, this is all post-processing. There's an absolute slew of things available for post-processing. Now we're starting to run out of time a little bit, so I'll just quickly get to the final results of this, which shows you the, in this case, it's plotting the von Mises stress here. And you can see that the bottom and the sides are sort of being held in place. There is some stress at the top of the sides because the tops are free to deform as per our boundary conditions, and you have this massive variation in the shape of the resistor beam, and this is where the highest stresses are as well. Now this looks like perhaps our assumption of a linear elastic material was not very good, but this is just the automatic deformation node, which shows you this deformation has a very large scale factor added to it to exaggerate the deformation and make things obvious. Set that to 1. Plus again, suddenly this looks more like we might expect from linear deformation in a linear elastic material. However, if you zoom in, you can still see that there is some deformation there. Yeah, so I think that's the end of the live demo. So what I'll do is I'll nip back to the slides. and we can go through to sort of the ending slide. So this was just an introduction to COMSOL. For those of you who already use COMSOL regularly, it might have been a little bit sort of, yeah, I know that. But for those of you who don't, hopefully it was more useful, and it sort of helped you understand, first of all, what COMSOL is and how it might be used. There is a very large selection of further resources available on our website. Things like there are example models and applications. You're going to see some example models later. They often come with instructions regarding the physics related to the model and how to set up the model. We've got the Learning Center, we've got blog posts, and there's technical support. So this is something we wanted to point out. PhD students are entitled to use technical support. So if you have an issue with your model, say something's not converging and you don't know why, or something is not behaving as it should, or perhaps you don't quite understand how to implement a certain feature of physics into your model, you can go to COMSOL, www.COMSOL support. If you have a COMSOL Access account, you can contact support, and we will help you as best we can. And just, to say again, everyone from PhD students, postdocs, lecturers, etc., in industry, you're all entitled, as part of this license, to use COMSOL support. So that's the end of this introduction live build. We're going to have just a quick time for Q&A here. I think I went on a bit too long. But the next session will be high-frequency electromagnetics at 11. That'll be followed immediately by low-frequency electromagnetics, but there'll be a break at 12:30.
Thanks, Joseph.
That's right.
So, just quickly before we do the Q&A, there's a couple of things I forgot to point out. So, firstly, you can see the schedule here. You don't feel like you have to come to every single session, just come to the sessions that you're interested in. The other thing that I should say as well is I've got a few feedback forms here, so if you are leaving, I'll leave these over on the table over here, and if you could fill those out, that would be really helpful. And I know that not everyone here is actually a member of Newcastle University, but those of you that are, I don't know if you're all aware, but there is a pre-existing license agreement with Newcastle, so you should be able to get access to the software fairly simply. If you need some support with how to do that, you can contact myself. My business cards are here, and feel free to contact me there. Other than that, if you do have, there's obviously a Q&A session at the end of every session. But if you do have a burning question during the talk, you can put your hand up and ask. That's absolutely fine. Thanks for the talk, Joseph. If anyone has any questions, go ahead.
Oh, yes.
So my question relates to the access to the software.
Oh, right.
Oh, right, yes.
So I work at Newcastle.
Yes.
I'd like to access COMSOL.
Yeah.
I have absolutely no idea how to do it.
Okay.
Do I download it onto my laptop? Do I access it through a server? Can you just give us the idiot's guide for 2 minutes?
So essentially the best way to go about it would just be send an email to the IT support services, and they'll basically get you set up with, they'll talk you through how to get it set up. I don't know the details of how it works within the university. Patrick maybe does.
Yes, so I think we've got something, it's a 40-seat license?
I think it's only 20.
It's
but
only 20.
I don't know how
I
many.
thought it was 40. But anyway,
Okay.
we've got a multi-seat license here in Newcastle. We can, given that we've got a certain popularity in the room, we can broaden it out if required.
Mm-hmm.
So at the moment it's sitting on all of the common computers within the university. There is a kind of an RDS desktop thing where you can access the common desktop from the comfort of your home. We can get IT to install it in our standard computers within the university. I'm not sure what the situation is about downloading it at home and using it some kind of direct access. I don't know about the license there. But any Newcastle laptop, Newcastle computer, we can get IT to install.
We can get it installed on our own computer.
Yes, I think so.
Do we need to be on the university network to access it, or can we, once we've got it installed, can we access it when we're somewhere else?
So it has to connect to the license server.
Yeah, probably.
So I'm not quite sure on that count. I know that when you're in Newcastle, on Newcastle's network, it seems to work. Works on my computer, at least in my office. I haven't tried it at home.
It works at home.
Okay, there you go.
It does look around.
Where you get a countdown on your license. It's like 60 days, and then you have to refresh.
So
So it's got to be on a laptop to bring in to refresh it.
Yeah, I think so.
Yeah, presumably you have to be connected to the server to install it initially.
Yeah. Yeah, it's easy.
I hope that answers your question.
Yeah, related to that, are there any licenses for running on the HPC?
Yes. Yeah, so the license type that you have is the floating network license, which is sort of the premium license type, and that does allow for HPC and cluster computing as well.
So a single user could use 10 of those licenses?
Yeah, no, so there's no limit on like the cores that you can use.
Okay.
So one seat is unlimited cores.
Right.
It's just limited. The seat just means concurrent users, basically.
Okay.
So that shouldn't be an issue at all.
With the model that you were doing on the live build,
Yeah.
So in my sort of outpost of the university, we're kind of interfacing with industry around like prototype building of like actual things like power modules and stuff like that.
Yeah.
So when we're looking at like performance of potential design, from my perspective, I'm a process engineer looking at manufacturing, so I might want to look at things like if I have known if I put defect scenarios in there. So in my solder, your model is assuming like a zero void perfect solder joint, correct?
Yes, however, you can.
You can adjust all.
Yeah,
that
you can
stuff.
adjust.
Yeah,
You can.
okay, cool.
You'd need. So for those sorts of connection. Now, I'm not an expert on the structural mechanics part. Unfortunately, we don't have him with us. But there are boundary conditions you can place on internal boundaries, essentially. So you would be able to pick. I don't know which one it would be. Here, there are. It's a little bit more complicated in solid mechanics because the geometry can change and the mesh can change with it.
But in essence,
in
can
essence, yeah.
kind of like go worst case. Like if I was to say within my build specification, you are allowed voiding up to 20% or something like that.
Yeah,
I can
you can
model what the effect is of.
Yeah, you can model what the effect of these very imperfect connections. You can model what gaps be. You can even add features for sides that aren't touching when you construct it, but may be touching later, and the way the mesh will behave there. That does need the the structural mechanics module, but I think the license has that, doesn't it?
Yeah.
Because it's an F&O, it has. I think the BATR has essentially all of them, doesn't it?
Yeah. So
Yeah.
the
So you should be
license
fine.
includes at least one instance of every module.
Yeah, so you should be fine with that. If you are looking to do that, probably the best place to start would be the learning center. I can't tell you an example model off the top of my head, but there are some for each of these features.
I mean, from my perspective, I'm unlikely to probably be doing the sort of the modelling, as I'll be really more sort of looking at the actual like assembly of these products and stuff like that.
Yeah.
But it's just knowing that when we go and speak to clients and stuff like when we say we can do the modelling at the design level, we know that we can potentially model what could potentially happen in the build when we've got limited materials to work with.
Yeah, structural mechanics is quite it's quite well developed with features for things like that. It's one of the sort of it's actually I think one of the earlier parts of the COMSOL library, I think, but it is well developed on stuff like this, and everything required to actually have the model running in terms of the mesh is also set up. You can also do with for this and have like moving meshes and things and deforming meshes during the study.
With and on top of that as well, with like importing stuff into the libraries and stuff like that. So when companies like chip manufacturers, like component manufacturers produce devices, how can we get accurate models from them? Again, like rather than sort of like we have to kind of reverse engineer what they've built into the system. Is there how's that kind of?
Yeah, so it's sort of the geometry import is designed sort of for imports of CAD files. So if they do have a CAD geometry of that, you can just put it straight in. Something else you can do, which we'll talk about now, is you can actually import a mesh without a geometry.
Okay.
So you can import, say, a 3D scan of the object as a mesh, and then you can build the geometry from the mesh. Because if you think a 3D scan is far more like the mesh in its construction, you've got these sort of sets of shapes and which are built together. You can import that into COMSOL as well. That's a little bit more advanced, but there are tutorials available from our site on how to do that, how to repair them properly, and then how to create geometries and add physics to them. Yeah?
to suggest or request other coupling methods?
Yeah, so there are quite a few. That was just showing what was available for electric currents and solid mechanics. So you have things like, well, if you have heat transfer as well, you get this thermal expansion. You have things like piezoelectricity, piezoresistivity. If you use the magnetic fields interface, you also get magnetostriction and nonlinear magnetostriction and piezomagnetism and things like this. So there are more. It's just only going to show you the ones which are relevant to your sets of models. If you do want something that doesn't exist yet, or doesn't exist in the form that you want to use it, you can come to us on support, or you can just feedback as product feedback on the website, I think, or to Alex, really, that this would be a good inbuilt multiphysics interface to add. But what you can do in the meantime, and you do need to be a little bit careful in doing it, but it is possible to do it, and once you get the hang of it, it's reasonably straightforward. You can add mathematics. So you can add your own PDEs, ODEs, etc. in, which will allow you to take a variable from one interface and add it into the COMSOL solving in terms of the other. So you can couple them manually if the coupling doesn't exist. It's a little bit more involved, but it can be done. There are tutorials on it. But yeah, if you find something that you think would be a very good inbuilt multiphysics coupling, you can always feed that back to us, either in support to Alex or on the website. Yeah?
Yeah, just very briefly. I'm not sure if you're on the internet, but could you just do a quick run through of the website?
I'm not on the internet, I'm afraid.
Okay. So it's just worth noting that there's lots of tutorials to this online. You've got a big library, so if you were on the internet, it would be worth showing that.
Actually, what would be good?
Wi-Fi, I think.
Yeah, but so without the internet, if you've installed COMSOL, you have the option to install this applications library. Here are example applications, pre-built example applications. So I go into AC/DC and I don't know, let's look at capacitive position sensor. Yeah. This is a model that COMSOL has already built to show off something. It's to show off a feature or an application of COMSOL. You can open this PDF document. This is saved locally, that's why I can do it, which contains an explanation of what's going on, sort of details of what's happening. It's crying out loud. What's going on? It contains explanation of the physics and results that you'll get, and it has modeling instructions, step by step, so you can recreate, or if you find something, say, a little bit challenging and you're looking at the example model and you go, I don't see how that has happened, there are full instructions for these example models. And I can, so for example, open this, and here's the example model, all set up, in this case with its results, with its study, and with its physics. And they are available usually on, it depends on whether the option's been ticked on the install, essentially, as to whether the application library is there, or whether it's there incomplete, or whether it's complete. You can, I think, edit it and download it on COMSOL, but all of those library models and more are available on the website.
Yeah, no, the website is very good. It's got a very comprehensive database of resources. There's plenty of tutorial videos for just about every module that we have. We've also got blog posts, like it says. You can go through this application library also on the website as well.
Yeah, it's bigger on the website.
Yeah, there's even user stories and technical papers as well.
Yes, so those 3 user stories I showed you are just a couple of examples of these articles available on the website, which have been written by customers about what they've used COMSOL for. And there are loads of those available, actually, aren't there?
Yeah.
So I just picked some I like.
We do encourage people to take a look at the free resources on the website because they are very good and they're free. So yeah.
It's also worth noting that COMSOL has quite a large community around it as well. So if you can't find something on the website and you don't want to access support quite yet, you could always just search on YouTube for a tutorial and someone may have done something, because COMSOL has quite an active community around it.
We don't take responsibility.
Yeah, that's not. Yeah, that's not. They're not affiliated with COMSOL. They're just doing similar things to you. That's sort of like going and asking someone else for help. So If they tell you to do something and it's wrong, don't blame us.
For the most part, we have our own videos as
Yeah,
well.
we do.
though,
We have
so
our own.
We can vouch for those ones.
Yeah, everything that's on our website is vetted. Anything that's elsewhere may be useful, but isn't vetted.
So I don't know if there's any more questions at all.
I'm more interested in the chemical reaction engineering model actually. So can I ask whether that's just limited to homogeneous reactions, fluid phase, or does it do heterogeneous as well?
So none of the three of us here are experts in the chemical reaction engineering modules, I'm afraid. Yeah, see, in the chemical reactions, it's not just homogeneous reactions, to my knowledge. And there are multiphysics couplings with, say, the CFD module for doing fluid flow. As I said, some of my examples were coupled chemical reactions and fluid flow. Sort of further examples.
You can do non-isothermal reactions, and you can do
Yeah.
reacting flows and that sort of thing. But
Reactions in turbulent flows.
yeah,
You really
none
wanted
of us
to-
are really experts, so
We're
I don't
not.
want to go too deep into that.
So one of my PhD students has done this. So we've looked at implantable fuel cells to look at, harvest, so it's vampire fuel cells that can harvest energy from the blood supply.
Right.
And in that scenario, we were looking at, having this multi-plate stack array of these micro-sized fuel cells, and we were looking at the diffusion of glucose and oxygen in, and then we were looking at then these multiple reactions that were going on between the fuel cell plates. So yeah, it is possible. Now we did it in a very simple way. We're not, it was the first attempt at running COMSOL and chemistry. But for us, but yeah, it is possible to have multiple reactions in there and have them coupled, because there was a number of reactions that were dependent on each other and dependent on each other's concentrations.
Yeah.
Yeah.
I think we had a question at the back.
I have a quick question about the interface. Is the license that we have bringing the interfacing with MATLAB and simulating, because I assume this will give you more control over the model itself and also answering the pointing question, because then you can build your own things in the other modules?
Yeah, so like I said before, the license agreement we have with Newcastle does include at least one instance of all of these modules. So that includes the interfacing modules as well. So say you're using MATLAB, the nice thing for MATLAB, it allows you to sort of two-way couple the two softwares together. So if you make a change, you can have them linked. So if you make a change in your MATLAB model, it will automatically make the same change in the COMSOL model and vice versa. So you can link them like that. Yeah, and the same goes for stuff like Simulink, SolidWorks, all that sort of thing. So yeah, that should be available to you. That's not a problem.
What do you mean by at least one instance?
Yeah, so there's not necessarily 20 seats on all of these different modules because they're not all used by everyone. So the more popular ones will have more availability, and the less popular ones will have less. But the idea is that if someone wants to do some sort of physics modelling, they should have access to it. So there's at least one instance. And when I say one instance, that just means one concurrent user.
Yeah.
So if you're using a very niche, say you're using the uncertainty quantification module, which is quite rarely used, there might be only one instance of that, but there's very unlikely to be someone else using it at the same time. So you should still be able to access it. Yeah, that's what I mean by that.
Again, it should be noted that we got the site license for COMSOL last year, and we took a smaller number of seats, because we don't want to be wasting money as Newcastle University.
Yeah.
If there is a very, very broad interest in this, we can expand. We can
Yeah.
just ask IT to expand. But we don't want to be spending a lot of money on lots and lots of seats if people aren't using it.
Yeah.
Hence, this is part of today's exercise.
Yeah, and we do actually have the renegotiation coming up next year, so it'll be good to know what the usage is looking like a bit before that comes up.
Yeah.
Amazing.
How would you know if you have more requests than seats?
Sorry, say that again.
How would you know that, I don't know, let's say 10 people want to use Lightning in MATLAB and we have only one?
Yeah, so I think it will come up with an error message saying this has already been checked out, this module. So I think when you access COMSOL, I think Patrick probably knows the details.
Yeah, there's a little error message that pops up on your screen.
I know. I have the error message, but how does IT know that there are actually 20 who request the access? so that they would know there is no request.
So I'll be leading with a couple of other people, but I'll be leading the negotiations with NYT.
So the complaints go
So,
to you.
so you know, just let me, you know, so during, at that time, when we get to this renewal, I'll send an email out, and like, just let me know. Yeah.
Any other questions?
Can we have a comfort break?
Yes, we have got a 15-minute break scheduled, so we'll be coming back at 11. I don't know, I did hand around a registration form at the start, I don't know where that got to. But if you could try and sort of sign your names on there so we know who's arrived and who to send the slides and the models to, that would be fantastic. Otherwise, I think we can take a break and we'll be back here at 11. Cheers.
Yeah.
Yes, because you have to do oh, thank you, you found it for me.
Toilets are just upstairs. There's downstairs as well. There's just upstairs, and there's a kind of coffee area as well.
Okay.
If you guys need it. Oh, looks like everybody did show up.
Yeah. See how many people are here. Yes, it's here. Yeah.
Sure, yeah.
Lovely, thank you very much.
Yeah, that makes sense. Are you going to leave your laptop here?
Yeah, I'll probably just leave it.
Yeah, that's fine. Well, the problem...
I can unplug mine and plug yours in.
You are sorry?
I can unplug mine, the word's phone there, so I can unplug mine and plug yours in.
Yeah.
You can actually just leave your wires over there if you really want.
That's true. I wonder... Okay, I'll see. I think we have space.
Yeah.
I have a very technical doubt. Of course, I'm very new to the modeling. So basically, when you call it as an error, what is the error it is people?
An error?
Error, like for a
Any
convergence map.
Oh, it would be... So,
you take a
it's
simple
sort
example.
of like this internal error, this internal variation from the net through previous iterations. So he's going to talk a bit about studies and solvers,
Right?
And he's going to talk in terms of the. This is going to be mainly in terms of the iterative solver, about the Newton-Raphson method, and about what the error is in there. So the error is defined in terms of the numerical method that's being used to simulate it.
Sure.
So it's essentially this sort of internal consistency of the results. He makes small. It's sort of like you make small perturbations, how different the results.
So for example, let's say, I want to look at a waveguide, wave mode propagation to a fiber, in a simple example.
Right.
So that's an electromagnetic wave.
Yeah.
So when I'm just trying to model it, what kind of parameters error that I'm going to get, and how I define that. I mean, tolerance can be defined as a relative one.
Yeah, it generally is a relative one. So these errors that you're seeing are sort of relative errors. So if you think about 10 to the minus 3, that's sort of like the numerical error is on the order of the third, fourth decimal place of a number. Of a number in the independent variables. So I don't remember what you're solving for in the way that it works.
It's electric field.
Is it just electric
Yeah,
field?
electric field.
So I mean the value of the electric field.
And the tolerance is what, like 0.001?
Something like that.
Yeah,
I think you can change the tolerance.
You can change the tolerance, but it's normally just leave it there. That's normally good enough.
So you change the tolerance, you can end up with more accurate results, but you can also have issues with convergence because the level of numerical error is inherent in the setup might be higher than the tolerance that you make.
And if you try to put it too low, you just
Yeah, you try and put it too low. If you try and put it too low, you'll just I'm there, I'm done. And it's not done.
No, definitely. That's why, because I was using barely like some pattern-based simulations. When we go for like a very ambitious error values, like for example 10 to the power of minus 5, 10 to the power of minus 6, it wasn't conversing and used time.
Yeah, as I say, COMSOL is not calculation software. So there's software which So, for example, in my PhD, I wrote a bit of calculation software, and the idea was to do a quantum mechanical calculation with a numerical error that had like 10 to the minus 10, 10 to the minus 12. Yeah, but that's highly specific software, and usually it's focused on the exact set of problems. COMSOL isn't like COMSOL simulation software, so it's usually a higher error, but more general and larger. It's not producing a single value, it's producing values of fields.
And typically, what is the publishable error for?
I don't use
Publishable depends on your fields. That's what you're
should be able to
doing.
apply voltages and have
The errors in COMSOL are usually sort of the default tolerances are around sort of 0.1%. That's sort of, yeah, it's sort of that level that you're expecting UX to be. If you have a very large variation of scales across something, I've seen people have numerical variation with larger values, which kills numerical variation. But yeah, what's publishable depends on what you're doing.
That's why I was given. I mean, I'm giving an example of electrical.
Yeah, but people do publish based
I'll
on
check with Joshua in a second.
people have published.
He spoke to us recently, so he might know better than me.
Okay,
If
so
even if there isn't,
I
you
did
can
this
use
and
the
I
fine.
used
You
this
don't necessarily have to use
COMSOL, I
the
used to convert the
You can write your own
Here it is.
equations that link different interfaces. So in the example of the electric current, you didn't need to use the multiphysics or something. You could have had a heat source that referenced the loss variable from, so you could do user sign coupling. You know, in the semiconductor interface, does it have a multiphysics coupling with AC/DC?
Yes,
It
it
does.
has a multiphysics interface with electric currents.
Electric currents.
I don't know if you can do electrostatics, but definitely electric currents. It can't do magnetic fields because, well, it can, but it can't because it can take a current in a way, and you get a voltage from that, so you can do MEF. But it assumes zero magnetic fields. The actual semiconductor interface works in terms of zero magnetic fields because the assumption is based upon the semiconductor interface itself.
But I'm wondering more about whether you can properly couple the electrostatics with the semiconductor. You have a semiconductor which is a gate which has trapping, and then you add some incoming wave.
I think you can do that. It's a shame Nat isn't here. Yeah, I think it can definitely couple with AC/DC. I don't know if there are couplings with RF. We'll explain a bit in the next session, but AC/DC is sort of the low frequency. It sort of assumes no wave-like behaviour. So it definitely couples with that. You can also couple AC/DC to RF, I think.
Yeah.
So this might have to be user-based.
I definitely think what you're saying is doable. Whether it's predefined or you have to define it yourself.
I think it's doable.
So is there somebody I can talk to?
If on supports,
Yeah.
Nat, essentially if you ask anything about semiconductors, it'll end up going to Nat.
I'll go to Nat. Who does,
Yeah, and he knows a lot. He's up on the semiconductor module. He knows he's very sort of experienced in it. Yeah. So that he would be a good person to talk to. Nat James.
Yeah, Nat Davis. But I mean, if you put it into COMSOL.com/support, it'll go to.
You ask a question, it'll go to Nat.
Have you ever used the support before? It's not.
So we have the teaching. I'm from Darwin University. We have the teaching license. We use it for semiconductor teaching in our third year undergraduate module. But I would like to include something a bit more complex and a bit more involved.
I think you should be able to access support on a teaching license. I think the students can.
I mean, we do have a floating license
Oh yeah,
for research as well.
yeah. You can definitely access support. Yeah, you'll definitely be able to access it. Yeah. If you have issues with semiconductors, put it on support and Nat will answer. And
Thanks, Austin. Cheers. You had a question?
Yeah. So you've done a great job, as in giving us, the kind of insights, to the COMSOL again. Yeah, I was once carrying out a research on this internal combustion engine.
Okay.
Yeah. So I was by my supervisor there, and I was asked to use of COMSOL. COMSOL should be able to carry out the work. Okay. So when I was using the COMSOL there, I usually get stuck at this convergence points. So while running the simulation after coupling, using all the physics and then coupling with the model, right? So I have issues with the convergence,
The converge. Okay, so I think the first is mesh. A finer mesh can sometimes improve convergence.
Yeah.
It'll make it take a lot longer, and especially along the memory, but it can improve convergence. It may be a solver issue as well. So it may be that the shape of your geometry is such that you end up with bad mesh elements in various places, and sometimes there's not a lot you can do about that in the mesh. Taylor's going to talk about this in the final session of the day. You can go from an iterative solver to a direct solver. So the iterative solver works in the Newton graphs and it takes various steps. But the direct solver just sort of does it in sort of one go. And it is very memory intensive, especially for large systems, but it is far less sort of susceptible to things like bad mesh elements. So sometimes when an iterative solver won't converge, a direct solver will work. But you don't get the same sort of convergence. It's not working the same way. That's one option. If it's multiphysics, it might be worth turning off various physics interfaces to run to see if it's any of them in particular.
Yeah, it's incorporating more of multiphysics, the chemical reaction of the foil. Okay, coupled with some other boundary conditions and it transfer the free flow. Okay, so I couple in lots of equations in there.
Yeah. So
then the chemical kinetics,
yes, given that it sounds like quite a highly coupled and non-linear problem, I'm going to guess there's something in the solver.
Yeah,
it's something you need to do in the solver, and that can be a bit of an art more than a science sometimes. I'd try finer mesh in various places. Try turning off various things and see if it still struggles, because it may be there's an issue with like one particular element. Sometimes you need to do fully coupled rather than segregated solvers for multiphysics. Essentially, if after today you've had a look at everything we've said and you've tried various things and it's not working, you do have access to support, so you can go on the website and you can send essentially the model to support, and someone who's an expert on Bashir, probably Ross or something, isn't it, will look at it and will be able to look at it and work out why it's not converging. And if it is something odd you need to do with a solver, they can work out what that is and tell you what that is and why that is, and can actually get your model to converge for you if it's really struggling. So that is always an option you have. You can always go to support, and their job is just COMSOL. Our job is just COMSOL.
Also, in this area of biomedical,
okay.
Yeah, we try to also make it in modeling of this kidney nephron, kind of a free flow, like a sort of perfusion in the kind of kidney flow. Right?
Yeah.
So once I could not find something, a kind of similar model or something that will give me a kind of insight.
Fluid flow. I think we have a fluid flow example
We
in
have fluid.
artery or something.
There are, but sometimes the biological things are far less
To
example.
incorporate the biological system, the biological features, into such a kind of model or equation to be able to analyze that kind of scenario, like absorption, and kind of kidney during the fluid flow and the thermal condition as well.
It may be you need to use multiple examples for the different parts. So there may be an example which shows absorption, there may be an example which shows a different aspect of it, but not all at once.
It's basically the biological area. If it is the fluid flow, then I can see that there's an aspect of heat and fluid, which I can make use of the physics there. Okay, but the area of incorporating some biological features.
Yeah, there is stuff like porous fluid flow, and there are bioheat transfer and things like that. Yeah, there are interfaces which you probably need to look through them. I don't really know a lot about the biological part or even the fluid flow part. I don't know. If you haven't been able to find an example. But there might not be one on the applications library. It might be worth looking at the blogs. So for example, I'll give you an example. There's one about importing scans of bones and biological structures into COMSOL. That's all in a blog. There are blogs about that rather than an example, and they're very good blogs. So you might want to try the blogs page on the website, and if you search sort of generic terms related to what you're looking for, you may suddenly find, oh, this person wrote a blog on how to do this. Yeah, it's the biological bit is a bit less.
Yeah, we have a few examples, but it's not like we don't have a like biomedical interface.
Yeah, it's not the widest. It may be coming at some point, but it's not.
Discovered that there's no more of a biomedical engineering kind of application.
Yeah, it's currently pulling things from different
modules.
Yeah, there's no biophysics module at the moment. There might be in the future. I don't know.
I think that would be a very good.
It would be good, wouldn't it?
Yeah, something to look into.
Okay, that sounds good. Well, hopefully some of those examples.
Yeah, I'd do that. Yeah, and if you absolutely can't find anything, again, support might be a good place, because we have different tools for searching example models and things like this, and we have different
we've got like an internal
models available. Yeah, we've got all these internal stuff that we can look through, which it might be easier to find examples of what you're looking for, or to be honest, some of the applications engineers have been there so long, and they might go, oh yeah, I know exactly which model it is. It's this, which has happened before. Yes. So yeah, I think blogs make use of support. I think the blogs is a good place to look for stuff. Yeah, that's all right. All right, I'll let you start.
You guys can set up. I'm going to look for
Yeah, no worries.
Yeah.
Good to go, or is it?
Yeah, well, we got a couple of minutes, right?
Yeah. You don't need me to introduce anything this time, do you?
No, I think we're good. Mine doesn't have 2 ports, so I couldn't use it. I couldn't see a second port anyway.
Do you want the plug?
The plug? Oh, yeah, maybe. Oh, but I don't have a second one to plug it in with.
Oh, what? How old's your laptop?
I know, it's a bit rubbish.
Oh, it's a loaner. Do you have a different power adapter?
Oh yeah, I've got one over there. I think.
Is it a different end? Is it not USB-C?
Oh, it's small.
Oh, right.
I'll probably be fine for 45 minutes.
Yeah, I don't know where I've plugged into it. It's under the. Yeah, it's under here. If you need it. Do you want me to bring the power thing over?
No, it's alright.
Okay.
Well, if I need it. Oh yeah.
But yeah, you're looking at.
I'll bring it up.
You're in the order of like a few thousand. I don't know if that's sort of what you expected. I don't really know, but that's usually for personal licenses. No worries. Again, it depends on which type you get. I think what I think the business card and I can email you more details. Maybe I can spend a little bit more detail on what we have. Like I say, it's quite complicated, the pricing.
Right. Hello. My name is Taylor Boyd. I'm going to be taking this session on high-frequency electromagnetic modeling in COMSOL. So just to give an overview of how we approach electromagnetic modeling in COMSOL, we break it down into a few different modules based on the sort of type of electromagnetism you're looking at. So if you're doing low frequency, we're using the AC/DC module. These are sort of lower frequency systems where we're neglecting the full wave-like nature of electromagnetism, and you can then solve subsets of Maxwell's equations, which can make it a lot more efficient to tackle particular problems. So the sort of interfaces we've been looking at, like electric currents, and have been mentioned, like magnetic fields. These are within the AC/DC module, and it allows you to tackle a wide range of different sort of types of devices and applications, like power engineering and electromechanics, and simulate things like inductors, resistors, and capacitors. So that's not what we're going to focus on in this talk. That's the talk coming up after, actually, with Joseph. I'm going to mainly be focusing on the middle two options, so the RF and wave optics modules. So this is where we solve a full version of Maxwell's equations, accounting for the wave-like nature, which then puts some constraints on the meshing we have to use. So we have to explicitly resolve all the wavelengths in our system, which then, if we go to very large systems compared to the frequencies we're studying, can cause some meshing issues in terms of the amount of mesh elements you need and then the resulting RAM that would require. But yeah, so those are the RF and the wave optics. They are quite similar on their sort of underlying physics. They mainly are just slanted towards different types of communities. So the RF module has a few features and sort of choices made that aim it towards the RF and millimeter wave engineering communities, and make it good for designing things like antennas and looking at radar cross-section and looking at sort of metal waveguides and filters and couplers. Whereas the wave optics module is more for the optical community. So things are expressed in terms of the refractive index instead of other properties, and you can look at sort of, it has a few extra features we'll talk about later to allow you to deal with these sort of larger systems, which can be good for optical devices and more optical waveguides or gratings or lasers. And then if you have a very large system where the requirement to do your meshing would be sort of unfeasible, we have the ray optics module. So there you sort of are neglecting the full wave-like nature. You're now just treating the electromagnetism as rays that you release through your system and sort of use a ray tracing algorithm to track them through and how they refract or reflect off various features in your design. Yeah, and it's good for much larger optical systems like cameras, lasers, and spectrometers. So you lose a little bit of the physics in terms of diffraction, but you gain sort of an ability to deal with larger systems. And as COMSOL is a multiphysics software that we sort of focus on that sort of phenomena, all of these can be linked with other areas of physics. So the bottom bullet point here for all of them is the linking with heat transfer. So you can take the losses that occur in these systems and then apply them as sort of heat sources to try and see what sort of heating might occur, but also you can do the two-way coupled analysis where you can consider, especially for things like stop analysis, how is that thermal load going to deform my system and how might that deformation affect the performance of it? Is my lens system going to heat up so much that it doesn't work anymore? So stuff like that. Okay, so yeah, just a bit more on the contrast between the RF and the wave optics modules, because they are quite similar. We typically recommend using the RF modules for domain sizes comparable with the wavelength, and its sort of difference, the key thing that it has with comparison to the wave optics module is lumped ports and elements for representing sort of feeds or small little capacitors or inductive elements in the system. Whereas wave optics is for much larger models, like a sort of optical waveguide in the image. And we work in terms of optical terminology, so we specify things like wavelengths rather than frequencies. And the material properties are by default specified in terms of the refractive index. Okay, and then in terms of, as we mentioned, the difference between ray optics and wave optics. Wave optics is a full wave formulation, which is required if you're looking at things like diffraction and the interaction with small objects, but it puts an extra constraint on your meshing, which is why sometimes we have to neglect it. Go to the ray optics approach, where you can see we're now just treating the waves as a series of sort of rays that trace through the system, and they can interact with objects, but you're not seeing the sort of diffractive effect. But so it can be a lot quicker as well. Okay, so we'll talk a bit about all these different modules. So the RF module we're talking about first. As we said, you can look at a whole wide range of different devices. So common sort of things that we simulate in the RF module are things like antennas, there's a few different features like the far field domain, which allow you to get extra useful information for antenna analysis, things like the directivity and the far field behavior of your electric field. You can look at scattering problems. We have particular sort of interfaces that are more efficient as well if you're doing scattering problems and you don't want to have to use the full wave approach. You can look at electromagnetic interference, power dividers, filters, and as we've mentioned, you can do multiphysics problems. So we'll come on to that a little bit later. But yeah, so each module is a sort of broad area that you're approaching, and then within that you get a few different physics interfaces which define the particular approach you're taking to solving the problem. So within the RF module, these are the physics interfaces that we have. So the frequency domain is one of the most common. This you solve using a frequency domain approximation, which gets rid of your sort of time gradients. You choose a series of frequencies you want to consider the response of the system at, and solve the Helmholtz equation. And then your mesh is then going to be dependent on the largest of those frequencies that you've considered. And you can do things like mode analysis and scattering, and look at periodic problems. If you want to do look at the time evolution of the system, we have two extra interfaces, the transient and the time explicit. So here you're looking at fully time domain problem. The difference between these is the sort of time stepping algorithm that they use in the solvers themselves. So the transient uses an implicit time stepping, which is a bit more robust. It allows you to look at things like nonlinear problems. So if you're looking at nonlinear effect, then transient is the interface for you because frequency domain is assuming linear behavior. And then you can solve for the time evolution of your system. And you can look at things like dispersive materials and devices and nonlinear optics. So time explicit uses an explicit time stepping, which doesn't support nonlinear phenomena, which is its sort of disadvantage with comparison to transient, but it does scale a lot better, so it's a lot quicker for larger systems. So if you're looking at the time evolution of a sort of large linear system, then time explicit is typically the best way to go. And then with all of these, we also have the electric circuits interface, which will come up in the AC/DC talk as well. This is a sort of lumped circuit calculation. You define a series of 0D nodes, which represent circuit elements that you connect together in a sort of typical circuit diagram way. And that can be used to either drive or be driven by your full finite element method model. Okay. So yeah, those are the various different formulations we support. In terms of the material models, there's a variety of these as well. COMSOL is quite flexible in how it allows you to define your material behavior. So as we've sort of already seen, there are the default material properties choices that COMSOL will request from your materials, and you can modify those properties to use your own user-defined values if you find that they don't sort of match with whatever you're looking at in reality. But you can also make them more complex. They don't have to be just single values. They can be functions of either space or time or other variables within the model, temperature, or in the case of RF, maybe electric field or the strength of the field. And so you could use it defined in that way. You can also make them anisotropic as well. And we have these predefined material models that either you can just work in terms of different properties if that's more convenient for you, so you can work in terms of permittivity or refractive index, or you can start to introduce sort of loss models, either via a loss tangent or a dielectric loss. And also there's the option to specify a dispersion model, so frequency dependence of your material behavior. Okay. So in the RF module, it's quite important how you represent your metallic surfaces. They're sort of quite dominant in the behavior of your systems. So we have a few different boundary conditions and domain conditions you can use to simplify this. So if you have something in your system that behaves as essentially a perfect metal, we have the perfect electric conductor condition. So that can be applied as a boundary condition on the exterior of that domain. And typically then you would neglect the interior because the fields will just die off instantly. So this is then represents that material as lossless and impenetrable. And having a much larger skin depth than the sort of characteristics, the dimensions of the object. You can also use the impedance boundary condition, which is similar. You sort of apply a boundary condition just to the exterior, but it will take some material properties from the surface and use that to calculate a sort of loss variable on that surface due to sort of skin effect behavior. And then if you have a very thin sheet of metal within your modeled geometry, you can represent that using a transition boundary condition. So similarly, it'll give you some lossy behavior due to the sort of skin effect, and it'll also give you a inhomogeneous sort of electric field either side. It'll be discontinuous is the word I was trying to use. Okay. So in terms of exciting the model, there are a few standard features that get used. So we have the port, which is, if you're doing something like a waveguide, then you would use ports to define the input fields, and you can use multiple ports if you have a more complicated input. And for sort of standard cross-section ports, the sort of analytical modes that are already sort of known can be just specified by choosing the mode number. For more complex port cross-sections, you can solve a boundary mode analysis to find the mode and then use that input into the system. And you can also use a periodic port as well, which is helpful with periodic structures. It'll automatically sort of take the incidence of your electric field and use it in your periodic condition to make sure there's the right phase shift, which gets used a lot in metamaterials. And then if you are doing something like an antenna, we have the lumped port, which defines a sort of small little electric field, which is a sort of lumped source of energy in your system, to then excite your, in most examples, it is an antenna sort of system. Okay, so a few other features that you can use. You can define a background field excitation. So this is often used in scattering problems. If you just want to say that you know there's an electric field or an electromagnetic field that exists and you know the expression for it, you can type that in as a background field in the physics interface, and then the interface will decompose the problem into the background field and the scattered field. So it'll solve for the scattered field and then it'll do the summation to give you the total field as well. So it's typically used for scattering problems, but can be useful in others as well. And then because often your RF problems, you want to look at your device radiating off to infinity. You don't want to consider the sort of reflections of exterior boundaries. We have the perfectly matched layer, which also pops up in other areas of physics, but this acts as quite a strong absorbing condition. You apply it on your exterior domains, and it will apply a sort of scaling to the material properties and the dimensions, which will strongly absorb any outgoing waves, as if it was in free space.
So, sorry to interrupt. So what happens if you don't put a match layer there? Well, if you put no boundary condition, I'm just intrigued. Will that bounce then? What will happen?
Yeah, it would bounce, because COMSOL also always gives you a default exterior boundary condition, and in the RF module, it's PEC. It's perfect electric conductor. So it'd just be like it's in a cavity. So yeah, you just get a mess of a solution. Okay, yeah. In terms of the results, the RF module and the wave optics module solve for the electric field throughout the geometry, and from that derive various other variables like the losses and the magnetic field and the currents as well. But you can also extract a variety of other things. If you've used ports, then you automatically get information about the S parameters. You can evaluate the impedance and admittance. You can do things like Smith plots and export to touchstone files and look at the specific absorption rate if that's something you're interested in. And if you've included the far field domain, then you can do various far field analysis. Well, you get various far field analysis variables like the antenna gain and directivity. Okay. Yeah. And then as an example of the sort of multiphysics element, there's the electromagnetic heating multiphysics coupling, which will automatically take any losses due to either currents or dielectric losses and apply them as heat sources. So you can look at, these are all taken from example models, so either available in the library or on the website. So you can do things like look at a microwave oven heating up a potato, or the absorption ratio on a head model, skin cancer diagnosis as well. So it automatically sort of passes that loss information to the heat transfer to give you the sort of full electromagnetic heating behavior. And you can also look at things like structural deformations, especially if you're looking at sort of a cavity system. You could see how a sort of force on that cavity could maybe deform it, which then gives it a different characteristic in terms of the mode analysis. Okay, so that was the RF module. We'll talk a little bit about the wave optics module as well. It is quite similar in terms of the underlying physics and a lot of the interfaces, so there'll be some repeating here that I'll sort of gloss over. In terms of the sort of intended applications, we're looking more at sort of optical systems now, so still waveguides, but optical waveguides and couplers. Fiber optics are modeled quite often as well. Scattering problems and lasers and amplifiers. And you can also, if you go into the transient interfaces, you can look at nonlinear effects as well. But so when we get down to the interfaces, you can see there are a lot of overlaps. So yeah, the frequency domain is exactly the same. Very similar in terms of transient and time explicit as well. I think I skipped boundary elements when we went through it last in the RF module. But that's a sort of a specific, pretty much used for scattering problems. Instead of, mostly COMSOL uses the finite element method where it's breaking things, it's meshing throughout the full volume. This is using the boundary element method, so you only mesh on your surfaces, which can be very efficient for scattering problems where you maybe have very large free space regions where you don't want to mesh throughout all of them at the wavelength you're considering. So you only need to then mesh on the scatterers. But per mesh element, it is a lot more computationally heavy than finite element method. So if you're just doing a standard model where it's maybe fairly compact, you wouldn't want to use the boundary element method because it'd probably end up having a huge RAM usage. Okay, but yeah, that is also supported in the RF module. The main difference here is the beam envelope. So this allows you to sort of bridge the gap between the sort of wavelength or multiple wavelength sized models that you do in RF and the sort of much larger systems in ray optics. If you're doing a system where you know pretty much how the wave is going to travel through it, so something like an optical waveguide or other sort of optical devices where you're sort of funneling the wave through a system, you can supply COMSOL with a guess about the sort of wave vector and the direction of travel, and then it sort of decomposes the problem. So instead of solving for the full oscillation, it's just solving for the beam envelope, which allows you to mesh a lot more coarsely. So if you're in that sort of range of scenario where you know how the beam is going to travel, you can use this interface and it allows you to look at much larger systems. So, yeah. Okay. Oh, yeah, and then, so yeah, you solve for the slowly varying field envelope. But other than that, it is very similar in terms of the features that it uses as the frequency domain. It's just sort of a different underlying method, and you supply this direction here at the start to make the method work. Okay. And then boundary element, as I mentioned, this is for scattering, basically. You sort of would typically define a background electric field, you mesh your various scatterers that are in the system, and it should be a lot more efficient than meshing through the entire volume. Okay, one of the other differences, just a small sort of ease of life difference with wave optics, is because it's quite common for people to use background fields and use it to try and define things like Gaussian beams. These are sort of predefined for you. So there'll be an option when you go to the background field area in the interface to choose, say, Gaussian beam, choose how you want to sort of specify that beam, whether you use the sort of paraxial approximation or a plane wave expansion, or you can use simpler things like linearly polarized plane waves or the other sort of plane waves mentioned. And then also you have the perfectly matched layer. So there's a lot of overlap. And similarly, you can couple it to a variety of different areas of physics. You can look at the effect of stress on the system, the deformation, and even you can use it to find things like a stress-dependent refractive index if you want. You can look at the heating, maybe to look at some laser heating and the effects there. Electro-optic modulation is where you sort of apply a voltage on maybe a section of the waveguide, and that can again, affect the refractive index, and you can maybe use that to control how a wave passes through an optical system. And you can even link it into the semiconductor interface if you are looking at the sort of smaller, finer behavior of certain elements. Okay, so just to sort of go on to the final element, we'll talk about the ray optics module. So you can see this is now moving to much, much larger systems, so things like lighting systems of cars, room lighting, cameras, telescopes, all these larger optical systems where if you were trying to solve every single wavelength throughout the system, the sort of meshing requirements are too large for any sort of standard computer. So instead you switch to looking at rays. So it has a wide variety of features that can help you here. So it's got a part library, because the sort of types of lenses that you use are quite common across different applications. You see it here. A part is essentially a predefined bit of geometry. You can sort of say you want a circular planar annulus lens. You pull that into the geometry parts library, and then use that in the sequence. And you can sort of parameterize it and choose its position. So it can make the creation of the geometry a bit simpler. It also has its own material library. So within the material library, it has its own folder with a lot of wavelength and temperature dependent optical properties that you can use. You can specify the release of rays in a variety of ways, either from a boundary or a defined grid. It'll then calculate the scattering of those rays at domains and at boundaries. And you can use boundary conditions to represent things like mirrors, gratings, and ideal lenses. And then it will automatically handle the sort of refraction and reflection and polarization difference at material boundaries within the simulation. Okay. Oh yeah. So this is the lens part library. So you can see what it looks like here. You sort of pull in you load it from the part library, which is sort of a pre-existing library of common lenses. This is also available in other areas of physics. It's sort of common pipe joints and things like that for other areas of physics, but it's quite often used in ray optics. But you see it comes in with a variety of input parameters you can specify, and you can tell it the sort of orientation of the part and where it should be placed and the sort of displacement from that plane potentially. And then you sort of pull it into the sequence to build up your full geometry.
And just a quick, I'm sure you'll pull this up. So, I mean, one of the key things within, simulation lens is to look at chromatic aberration. Where basically the refractive index changes with wavelength. Is that? I mean, if you pull off these lenses, will they have a refractive index built in that will already vary with wavelength?
Yeah. Well, it depends what material you use, I guess. These are the geometry. Yeah. Then you'll assign a material to them. But most of the optical materials, have a wavelength-dependent refractive index. Yeah. Okay. Okay. So and then ultimately it's working on a ray tracing algorithm. So you replace your full wave with a single ray that is traced through the system. It solves for the position of wave vector. And it detects the intersection with the various domains that you've defined, representing your lenses or other aspects, and changes in material properties. You can also, if you choose as an option, to add additional equations for each ray, which will increase the sort of computation time, but allows you to also consider things like the intensity of the rays and the polarization, and how those change throughout the system. Okay, so that was the ray optics. We've talked about quite a few different modules. Just to show you one of them in action, I'm going to talk about the microstrip patch antenna. So this is one of our application models available online and in the software. It's an antenna, a patch antenna. We're representing the sort of metallic aspects because they're very thin as compared to the skin depth is just perfect electric conductor boundary conditions. We'll excite the antenna using a lumped port, and then use a perfectly matched layer around the exterior to exclude any reflections from the exterior, and then we'll include a far-field domain feature so that we can get some far-field variables that you'd commonly want if you're looking at antenna design. Feel free ask any questions about the slides or during the demo, but I'll get into it now. Oh, it's already up. Okay. Okay, so yeah, like Joseph said, if we're making a new model, we can go to File, New, and go to the Model Wizard. Then we can choose the space dimension we want to work in terms of. So in this case, it's a 3D, fully 3D geometry and problem, so I'll choose 3D. Then you get your menu of physics, depending on the sort of modules you have available. So in this case, I'm going to go to radio frequency. I'm just going to solve for the behavior at a given frequency. So I'll choose the frequency domain interface and add it. So you can see we're solving for the electric field. Then I can go study and choose frequency domain. No. Okay, so then I get my user interface. I've got my 3D component, which I can add various features to, and my physics interface. Yeah, so you can see here that in this case, the default exterior boundary condition is perfect electric conductor. So yeah, in terms of one thing that you typically do, which is useful, allows you to do parametric analysis and makes it a lot easier to modify your designs after you've built them, is you can fully sort of parameterize your whole model. You can define various inputs and dimensions in terms of parameters. So I'm going to add some parameters here. You can type them in and their expressions, but I'm going to load them from a file. So I've got just a predefined text file I can pull them in from. As you can see, I've got things here defined about the sort of geometry dimensions, and if I was doing a scan of frequencies, then maybe the range of those frequencies, and the minimum wavelength if I was doing some meshing, custom meshing. So yeah, those are the parameters, and you can see the square brackets is the units. Then I can go to the geometry. Again, similarly to Joseph, just to sort of gloss over the geometry aspect of it, I'm going to insert the geometry from a previous example. In this case, I'll use the insert sequence option. So that allows me to just take the sequence from a pre-built model and just put it in and replicate it. So I can choose the microstrip. Usually it's just been made from a series of blocks. There, and a copy, and then we have a difference operation, a sphere. So the sphere here, we need to include an air sphere around the geometry to solve the electric field coming from the antenna. And one nice thing that fits well with the perfectly matched layer, which you use a lot, is within most geometry primitives, there's the option to automatically add a layer on your exterior. It's not very obvious at the moment. If I switch to the wireframe view, you can see that on the exterior of my sphere, there's an extra layer that I can just apply that condition to. Okay, so that's my geometry. So now I can add my materials. So I'm going to add from the library and use the built-in, which are sort of the most common. So I'm going to choose air, which will be most of my geometry. And then I'm going to use a user-defined material. So I'm going to use the blank option. So I can choose a blank material. I get a sort of material node. I can give it a name. So I'm going to call this substrate. There we go. Then I can apply it to this, these two domains here, which represent my substrate. And then based on what physics I'm solving for, it requests some material properties. I think I can remember these. So I'm going to give it a permittivity of 3.3, that's common, 3.8, and permeability of 1, and 0 conductivity. And that should be everything. Because the sort of metal elements here are going to be represented as perfect metallic boundary conditions, so I don't actually need to add a metal in the materials. Okay, so then we got our physics, which we're happy to solve everywhere. Don't need to change anything here. We got our sort of default material model here. So this is where I could switch to using things like refractive index or considering loss tangents, but I'll stick with the default choices. The perfect electric conductor is not going to matter too much when I apply my perfectly matched layer. And then the initial values, as we said, is not too important for things like frequency domain studies. Okay. So let's add our perfect electric conductor. So that's going to be sort of the top plate of the patch antenna, and then the ground plane will be these two other boundaries there. And then I will add my lumped port, which is going to be the excitation. It's a sort of connection, the feed for the antenna to this boundary here. And I'm happy enough with just a 1 volt excitation. So this, because it's a frequency domain problem, this will automatically just be the amplitude, and then the sort of frequency is going to come from the study. Okay. Before I finish, I should add the perfectly matched layer, so I don't forget. So because it's common to a few different areas of physics, this is not kept in the physics interface. It's within the definitions section. So you use this in a lot of different wave problems. You use this in acoustics as well. So I'll add the perfectly matched layer, go out and apply it to my exterior domains. Just a little bit of clicking here. Okay, so that should be all of them. Because it's based on a scaling, you need to tell it the type of geometry, so what type of scale it's going to use and stretching. So in this case, it's a spherical geometry. And the rest of these should be fine, the default settings for the scaling factors. Okay, and then the last thing I'll add, which I added that because it's sort of contextual. When you have a perfectly matched layer, the far field domain sort of sets itself up. It sort of applies itself adjacent to it. So if I add the far field domain, it gets applied to my air domain, and sort of underneath, you can see the calculation occurs on this exterior boundary, and it will sort of do an integration to extrapolate out that far field variable here, which you can drive a variety of other variables from. Okay, so in terms of RF problems and a lot of wave problems, the physics-controlled mesh, which is a default mesh, will take account of your physics when it's doing its meshing in terms of how it decides the size constraints for the mesh elements. So I'm not going to mesh just yet because I haven't told it the frequency, which I'm going to use 1.575. So it would have just used 1 gigahertz, which would have been fine. But in some cases, if it's way too, it was going to produce a really fine mesh, it could be a problem, could even crash it. So it's best to go and put in the frequency you're doing before you build your mesh. But yeah, you can see the meshing there. This physics-controlled mesh is quite good. It takes into account not just the things like the frequency, but features you've used. So the perfectly matched layer requires a specific swept mesh, which if I hide some stuff, so this is just a graphics tool to hide elements so you can look at stuff. If you hide that, you can see this sort of swept meshing is required for it to properly absorb. Okay, so I'll get rid of that. And also, it'll add like an extra little layer to make the far field more accurate as well. Boundary layer mesh. Okay, so that is the mesh. We're happy enough with that. In terms of the frequency domain, I could specify a whole range of frequencies if I wanted to look at the sort of behavior of a range here. There's even a range button. I could specify the start and end frequencies and the steps between. But in this case, we'll just look at a single frequency to get some results and to make it quick. So let's compute. Should be pretty quick, I think. All right, there we go. Okay, so yeah, you can see whenever COMSOL solves, based on the physics interface and the features you've used, it gives you some default results. Because they're default, they're not always the most well formatted, so you can see these planes are a bit in the way here. So this is showing the electric field, but the sort of X and Y plane aren't the most useful. So I could go into my sort of multi-slice settings and get rid of them to say that I want 0 planes there to have a better look. So you can see sort of electric field across my antenna. you can also modify these plots. You can, if I want to have a look at the sort of direction of the field, you can add things like an arrow volume. So let's add an arrow volume. So now, because it's an arrow plot, it's visualizing a vector quantity. It's automatically chosen the electric field, which I'm happy enough with. So I can then just choose the number of grid points. So I'm just going to look at one slice in the x plane, one x grid, and do 21, 21. So by default, the arrows are proportional, so they're just showing any arrows around the actual antenna. So I can turn that off to get a sort of more picture there. It's a little bit messy. Let's scale them down. But yeah, so you start to see a bit more about the field pattern throughout the system. I could also, just having them as red arrows doesn't look that nice. You can add attributes to your plots. So if I right-click this, I could give it a color expression, which then colors these arrows related to another variable. So in this case, again, I can just use the default, which is the field strength there. That's a bit better. But yeah, the other plots we've got here are related to far field domain. We can look at the sort of the radiation pattern, the far field on a slice, or in the 3D plot we get a full 3D visualization. So it's good to sort of get a picture of the directivity if you are doing something like an antenna simulation. And then if you have something, because we're doing a frequency domain simulation, this is a snapshot at a single phase, and we'd have lots of different phases where this would oscillate. So when you have something like that, you can do animations, which is nice. It gets you a sort of a better visualization of how the system evolves. So if I go to results and choose animation player, and yeah, choose the electric field. If I choose dynamic data extension, that just means it's going to animate over the phase that exists in the solution. Let's repeat forever. And then if I press play, it'll sort of generate a little animation for me in the user interface. You can also export these if I chose an animation file. It generates the same thing, but to a file that you could then use elsewhere. So yeah, it's just going through the different frames and putting them together. Should be done soon. So yeah, you can see it sort of oscillate there. You could play around with it so the arrows maybe look a bit better. And also probably exclude the perfectly matched layer. The results in the perfectly matched layer aren't actually physical. So one thing you could do is there's selections. So you don't have to plot the results everywhere. I could choose to select an aspect of the geometry. Maybe just look at the results on the air domain. That's made the arrows disappear for some reason. But yeah. Okay. So let me go back to the slides. So yeah, I think that's pretty much everything I have. The only thing, it's been well covered that the website has a lot of useful resources. But yeah, so if you have any questions about anything, feel free. Or we can... Any questions? Oh, sorry.
I might have missed it. With the ray optics module, and you're defining the lenses and things like that.
Yeah.
Can you have arbitrary geometry lenses? So deformable lenses, funny shapes that occur because of thermal effect.
Yeah. You can make you can make your own lens geometries, and if you include structural mechanics, you could have those lenses deform based on heat transfer and everything else. Yeah.
And the refractive index of the lenses and stuff, that's all multiphysics coupled into things as well. That would. Yeah.
It should map. It has a variety of different frames. It'll use the material frame to make sure that things work properly. But yeah, any other questions? Or we can take a break.
I guess if there's no more questions, we can take a quick break. I think the next session's at 4:15. That's quite good. That's quite good timing. Yeah, so we've got about 5 minutes. I don't know if anyone wants to grab a drink or a coffee or something, and then we'll start with the next session, which is low frequency.
The next session, 1:45.
1:45, yeah.
Instead of 1:15.
Oh, did I say 1:15? Sorry, my bad. I meant 1:45. quite bad.
Ooh, well done.
Yeah, you too.
I didn't miss the last time. I don't think I did notice.
Yeah, I don't know what happened there. I just had to quickly move on. Why did it disappear?
Sometimes it's something like, at least with Streamline, this might, yeah, sometimes it's something like,
Yeah.
I want to simulate this for.
Yeah, so
Can I ask you a quick question about simulating
Yeah.
seem to be that you do that not with the
I think it tends to be done in RF. Yeah, we have quite a few EMI examples.
Yeah, I know trying to simulate EMI.
No, that's absolutely really video.
Yeah, I think it's one of the things we do quite well. Yeah, because we do EMI. We even do, they started doing like lightning stuff. You can do EMI. You can do a line current that represents a lightning strike. Because we have an airplane example. But yeah, I think there might also be, there might be some ACDC now. But yeah, definitely something to do.
I guess the classic question is where the sort of transition between low frequency and high frequency sort of
But yeah.
What we find now with power circuits is we're getting higher frequency transients. Devices are more capable, they've got more amplification at higher frequencies. So we can get, I mean, that means we can get sort of like 60, 70, 80 megahertz, right, which is probably still somewhere low to that.
Yeah, I think that tends to be, yeah, it tends to be ACDC, or it could be very low RF. Yeah, there is definitely a crossover area where you could probably do it in either. You could either do MEF or you could do low frequency RF. So might just be wide
That sounds good. I'm looking forward to trying it.
Okay, I'm glad, yeah.
Yeah, I mean, I expect that the audio might come out of it.
I'm speaking sort of friends, I might not have all of the details correct, but I was trying to implement a perfectly matched layer in a photonic crystal waveguide, and was having some issues with reflection when the perfectly matched layer is in. So you've got
I don't have one yet.
You don't have one?
I don't have one yet.
Yeah. So I actually
and
probably
then
do need
the holes will extend into the perfectly matched layer.
Okay.
And I was wondering if there's a way to do this where
rather than just being I don't have a console pen. I've got
regular
I don't have a console pen. The only console stuff I have is a T-shirt and a camera.
I can't believe it's both covered in tea.
No, I mean, perfect match layers have to be homogeneous. They have to sort of replicate
I've got the
medium.
uniform on.
You've got the uniform.
Yeah, that was the issue.
I think Ollie's even got like a proper fancy COMSOL pen as well. I don't know where he got that from.
Yeah, essentially just
Lucky
extend
boy. Yeah, he had it done.
pull like a rod, which isn't what the rest
So
of the
you've
waveguide is.
Yeah.
the slides good.
Produce a lot of reflection. And if there's any way to have this absorb that, to not get reflection back into the structure.
Can you not do this as a periodic structure, or is it important that it's like a finite array?
It was important, yeah, because it was some large network with things connected together.
Okay, and why can't you just put the perfectly matched layer sort of out here?
Because they want to model it as if this is a waveguide that just goes on forever.
Oh, forever. Okay. Okay. But I mean, if you use a perfectly matched layer, then it's almost as if it is going to be forever, right? As long as you have a sufficiently large number of these things, they'll just get absorbed out as if it was passing out.
Yeah, but you were saying that it needs to be homogeneous at this region here.
So you'd have to put it like somewhere there, I guess.
Yeah, but then that would just be as if it was. If we say that this is air and this is silicon, I don't think that's what the means. But if we were to put it here, then that would just be as if this was air forever, wouldn't it?
Yeah, I guess. But I mean, it doesn't matter if it's just passing out and disappearing. I mean, okay. Well, I mean, feel free to pass it into spot. Oh yeah, sorry.
Looks like you've got a support question coming.
Yeah, potentially.
Or a question of one.
Maybe.
Also, when you're driving back to the service station, so much of
Yeah, you can. I don't know how to do that. I'm afraid.
It's okay, I could just keep drinking Red Bull.
Okay, that's alright. Sorry, I don't have to tell that.
Thanks a lot. It's really, really fun like, to hear like structure it happens, but yeah, it's amazing. Thank you.
Right. It's a little bit. It's a minute past quarter two. We've had a 5-minute break. Let's get on with low frequency electromagnetic modelling in COMSOL. So, with low frequency electromagnetic modelling, we mean things like modelling things like inductive devices and electromechanical devices involving time varying electric and magnetic fields. Or in sort of static cases, we have things like resistive devices, capacitive devices, and we can do things like magnetostatics as well. So I think the first question we need to answer is, what do we mean by low-frequency modelling? So suppose you have a device or an object you're modelling which has some characteristic length scale associated with it, which is a LC. Now we know from Maxwell's equations that changing electromagnetic fields will produce radiation. So this radiation, say, is produced at frequency f0, say you've got an AC system operating at this frequency, that sort of frequency. Then the free space wavelength associated with that radiation is lambda. Yeah. So if the device, this length scale, is notably smaller than lambda, here we tend to give the condition that it's less than 1/10 of the wavelength, then the effects of radiation are probably unimportant. Okay, there are situations where it may be, but it still is important. But generally, and for the devices we're going to talk about here and the modelling we're going to talk about, it's unimportant. And the device is sort of too small to see gradients in the wave, and you end up with this quasi-static approximation where changes in the field will propagate instantly across the device, and you neglect all this wave-like phenomena. Okay, you can still have time-varying fields, but you don't think about these spatially varying electromagnetic fields because the device is much smaller than the associated wavelength. You do similar things in other area of physics. So if any of you know in atomic physics, it's a bit like the electric dipole approximation, for example. So this means that we end up with this sort of, we can split this parameter space of object size against, well, operating frequency or free space wavelength into regions where we would say the AC-DC module is valid, which is for these low frequency in this quasi-static approximation, where the RF module is valid, and where the wave optics module is valid. So when we talk about low frequency modelling in the AC-DC module, we're looking at this region of the plot. Taylor's spoken about this region of the plot and up there as well. So if we move on, there are sort of 3 main study types available in the AC-DC module. There are others which do specific things, but these are the general 3. We have static, which in the AC-DC sort of language that sort of electrical engineers are used to would be a DC field. So the time derivatives of the electric and magnetic field vanish. It is this stationary case of stationary fields. We have the time-dependent case where the electric and magnetic fields are explicitly dependent upon time. So an example, you can model things like lightning strikes, say. But probably the most interesting and the most sort of commonly used, especially in sort of the more magnetic end, are the frequency domain. This what electrical engineers would call AC, where we assume a single operating frequency, and we model all of these fields as phasors, which are harmonically varying with this frequency. So all these time derivatives of these fields come out with this harmonic I omega term in front of them. You can replace them with that. It makes life a little bit easier and allows you to, it's essentially solving a stationary study with all these extra frequency terms and this assumed phasor behavior of these fields. So Taylor's just spoken to you. When Taylor spoke to you about the high frequency, he showed you 3 modules. He showed you the RF module, the wave optics module, and the ray optics module. And while they were similar in many ways, especially RF and wave optics, they were separate. In AC/DC, it is one module that covers the entirety of this sort of region of electromagnetic modeling. And so it has quite a large number of interfaces available to it. The reason for this is that essentially at this region it's all governed by Maxwell's equations. Ultimately, all these electromagnetism is governed by Maxwell's equations. But it's not always necessary to solve a complete set of Maxwell's equations, and it is often undesirable to solve a complete set of Maxwell's equations. So, for example, in the example I gave you in the first session of the resistor beam, we solve the electric currents interface. In the electric currents interface, we assume the magnetic field was 0. We assume there were no magnetic fields related to this current, perhaps this current was smaller than me, and we weren't interested in magnetic effects. So we couldn't solve for magnetic effects. Magnetic effects were not being solved for. This makes the solution actually much easier. It makes solving for the things we're interested in a lot more sort of straightforward. It means we need to worry a little bit less about some of the oddities that can arise when trying to form a well-posed problem in a full electromagnetics interface. So, for example, what I'll tell you right now is within the magnetic and electric field is the most general interface available in the AC/DC module. And this solves an ungauged version of Maxwell's equations, essentially. And it means you need to be very careful with how you pose your problem, because it's very easy to pose a problem that won't solve and that won't converge. In general, unless you're after some of the more niche features that are only available when you solve like this, you'd be far better off using, say, magnetic fields or electrostatics or electric currents. In general, when it comes to the AC/DC module, it's a matter of choosing the right interface for the job. You don't want to use a hammer on a screw. I didn't make that little graphic, but I like it quite a lot. So, what I'm going to do is I'm going to talk to you a little bit about the main AC/DC module interfaces. These are the ones that are most commonly used. They're the ones that are most commonly used in multiphysics interfaces with other physics modules, and they're probably the ones we see people use the most. So there's the electrostatics interface, the electric currents, magnetic fields, no currents, magnetic fields, and as Taylor mentioned, the electric circuit interface, which I'll go through a little bit more. Now, unfortunately, I'm not going to have time to give you a demo for every single one of these. It would take up far too much time. And to be perfectly honest, because they're it's the sort of module where you need to use the right tool for the job, all I'd be doing was teaching you how to use that interface, rather than telling you about the module as its entirety and what it can do. So I'm actually not going to do a demo, but I will be talking to you about example applications that are available both in the applications library, which I showed you, and on the website. So we start off with the electrostatics field. This is sort of the most simplified version. Here we assume that magnetic fields are 0, and we assume that currents are 0. There are no currents, there are no magnetic fields, it is electrostatics. It's ultimately governed by Gauss's law, and we solve for the electric potential in non-conductive medium. So I'll talk about that in a moment, actually. Study steps available. Stationary really is what you're going to use in this sort of study. There are time-dependent steps for sort of very slow variations and for various multiphysics couplings, but generally, if you're looking at sort of more rapid time variation, you're going to want to use something like electric currents or something like magnetic fields. Stationary is really where it's at for this. And the applications are for these sort of static electric fields in this non-conductive media, so things like capacitors, really, and high voltage equipment. It is what it's used for. So note I said it solves the electric potential in non-conductive media. And that's because in this sort of electrostatics approximation, if you have, in your conductor, what really does that look like? So charges will, in this limit sort of charges will move with gradients in electric fields, with electric fields, gradients in the potential instantly. So any conductor is considered to be an equipotential object and can actually be excluded from the simulation given the correct boundary condition. Use a terminal boundary condition, and you model that object, that conductor, that conductive object, as an equipotential, and you solve in the surrounding electrostatic regime where, with more interesting things with the electric potential is happening. So a good example from this that's available is actually the one I opened up from the applications library. So it's an example of a capacitive position sensor. So the idea being is that I don't have a picture of what the model itself looks like, unfortunately. They're just some results. The idea is that you have a I think it's 5 capacitive plates above a single ground plate, and that you have a conductive object moving in the vicinity of them. Using electrostatics, you can compute the capacitant across these 5 plates in terms of using terminals in terms of these lump parameters, and you can see how the capacitance across these plates varies as the object moves. So an example is this object is moving. It's changing position according to L, and we see how the capacitance on terminal 1 changes, which is the first capacitor, and then the capacitance on terminal 5 changes, which is the final capacitor, and how the relative change of the capacitance happens, and you can sort of see how a capacitive position sensor works. And this is actually modeling an example of a capacitive position sensor. For all of these examples are available on the website. They're available on the applications library if you want to have a look at them. It's a bit unfortunate that the end is right here, but they're at the bottom. The link to the to its location on the website and its application ID if you want to look it up on the applications library. So really, there's not a huge amount to say about electric charges. Really, the only there are 2 pitfalls. One is these conductive elements that you really want to avoid, treat as equipotentials, and use either a terminal domain condition to get rid of them or a terminal boundary condition over an element that is removed from the model. The second one is actually common to electric currents, so I'll talk about that with electric currents. So electric currents is sort of the next step up. We still assume that the magnetic fields are 0, but we can have non-zero currents. It's governed again by this, essentially it's Gauss's law along with continuation of charge and current and Ohm's law. And again, it solves for the electric potential, V. In this case, you have your sort of stationary step, but what you're mainly interested in is the frequency domain, the time-dependent study steps. They are the ones that people tend to use the most, and you can really see why. Again, a frequency domain step in terms of the AC-DC module is a lot like assuming an AC current at a well-defined frequency. That is essentially what it's for in this context. So applications for this are sort of things like static or transient fields in conductors. So we're interested in things like the conductive circuit and the resistor beam that we had earlier. The example is actually going to be a capacitor that you've put a time-dependent voltage across. You have a time-dependent voltage across it, for example. You're interested in the electric fields produced by current flow or relating to current flow in conductors. It's sort of the inverse of electrostatics, where in electrostatics you ignore conductors and treat them as an equipotential. In electric currents, you ignore perfect insulators. And you can treat very well insulating objects as perfect insulators. You can ignore them and you don't need to, because you're not after electric current in these objects. Yes, so if we move on, the example here, it's not my favourite example, but it sort of gets the point across, and I wanted it to be a frequency domain study. You have this sort of 3D model of a parallel plate capacitor in electric currents rather than electrostatics this time, and you model an AC voltage across these coils. You can then output the electric potential and the resistive losses in the surrounding air region, and you can compute the capacitance from this lump parameter, which you can get out of terminals called the admittance. This example also goes through adjusting solver settings for improved accuracy in these smaller values. It's worth mentioning now, Taylor showed you in his examples this idea that you often want to put a large air domain around your object in RF, because you're interested in how the field propagates away from it. Quite often you're interested in how the field propagates around an object in electric, in all of these actually as well. We weren't in the example I gave earlier, but we may well have been, as they are in this capacitor's case. So you may be interested in, say, you have a charge and you're interested in how the electric field varies for whatever reason, or you have some more complex set of charges. You would introduce an air domain around that as well, in the same way as Taylor did. In this case, the default condition is usually something like electric insulator, and all of these conditions are good. They are good boundary conditions at infinite distance. So there are two things you can do. You can either have a very large air domain so that the boundary layers, so that the external boundaries aren't affecting the field distribution at the center where your object is, or there is a sort of analog of the perfectly matched layer called the infinite element domain. So I don't have an example up on here because I'll be honest, I forgot about it when I was making the slides. But the infinite element domain you sort of add like a perfectly matched layer. It surrounds the object, then the the sort of external boundary condition can then be mimicked as being an infinite distance away. You do some coordinate stretching in the infinite element domain, which does that. Again, the results in the infinite element domain are not physical, so you want to ignore them. Just like the results in the perfectly matched layer are not physical, because there's some computational trickery that's going on in there with stretch coordinates and such. But that's actually everything. So actually, I forgot to mention, there is a pitfall with electrostatics. There is the same pitfall with electric currents. It's not as obviously a pitfall in these interfaces because of the way we normally think about them, and we normally think about them physically. And that is that these equations are all given in terms of the gradient of the dependent variable. V is always calculated in terms of its gradient, which means that ultimately it's subject to essentially a copy of gauge invariance, which is you can make any linear transformation of V that you want, and it will satisfy the same equation. There are, in a sense, infinitely many solutions to these equations. You have to fix V somewhere. As I did in my example, I set a ground, which set V as 0 in a given location, and I had a terminal, which set V as equal to plus 0.1 volts in a given location. If you don't fix the potential somewhere, COMSOL's going to struggle because the equations actually have infinitely many solutions, and it won't converge on one. It'll vary between them. This can happen with heat transfer as well. You need a specified temperature somewhere. It happens with the solid mechanics as well. You need to fix it somewhere, otherwise you have linear translations in space, again, which all solve the same equations. As I said, this isn't as big a problem in electric currents and electric charges because we think about these things in terms of voltage anyway. That's the normal physical way of thinking about them. We tend to think about potential differences across things, and we have set grounds in our mind. So we often put them in without remembering that that's what we need to do. That's not necessarily the case in this interface. So this is the magnetic field's no current. Yes?
Yeah, just before you get on to magnetics. Yeah. So for some of us, one of the problems that we have is that we're trying to simplify complex shapes and complex materials, in my case, biology.
Yes.
And, you know, you'd have some biological tissue, a big gunk, and it's got all sorts of different cells and different things in there. One way to simplify that would be just to make, you know, a 3D box with some kind of randomized variance of permittivity or conductivity.
Yes. Yeah.
Is there a way that you can literally make a box with a mesh with some kind of randomized variance?
Yes. So we haven't spoken about this, and we're probably not going to end up showing you it, so it's a good thing you brought this up. In the materials domain, we showed you built-in materials, and Taylor showed you a blank material. You can define material properties as functions. So COMSOL allows you to define functions. You need to be a bit careful because COMSOL sort of views these as pure mathematics. So it can take parameters, but it can't take variables and things like that. But you can define these functions, and you can make, say, your conductivity a function of position. And you can use either an analytic function, you can write your own form, where the input variables are position either in spatial frame, you can put them in the material frame. whatever you like, or you can use interpolation functions from data sets that you've got. So you might have, a data set which gives a random distribution of of conductivity across a given cubic volume, and you can put that in little.
So you can do an import?
Yes, you can absolutely. Yeah, you can import tables of data and it'll into functions. Yeah, it's a good thing you brought that up because I don't think either of us were going to mention it really, but it is there, and that's in the materials tab. So you define that in the materials material properties. Yes. So yeah, magnetic. So the first one we're going to talk about is magnetic fields, no currents. So here we assume this time there are no currents. J is 0, but B is generically non-zero. And in this case, we're actually ending up solving Gauss's law for magnetism. That ends up being the governing equation in terms of the magnetic scalar potential. Vm, if you've seen it before, it's often called phi as well. It's the same thing, they're just different letters, really. Magnetic scalar potential. Again, you have stationary and time-dependent steps. You don't really have frequency domain steps because you shouldn't really be interested in the AC case because you should have no currents, if that makes sense. If you are interested in things changing with time, you can use the time-dependent step there. But generally, things like the stationary step are very much good enough. The applications of this is usually things like static magnetic fields around permanent magnets, say. It's often quite used for permanent magnets as well, and for perturbations to external magnetic fields. You can use what's called the reduced field formulation to solve only for the dependent variable as a perturbation to some background field as well, which is quite nice, and this is a good way to do it. This is another interface which suffers from the fact that the dependent variable only appears in the governing equations in a gradient, so that you can have all of these linear variations, linear transforms of Vm, and it'll all solve the same equation. This is one to be careful of because we don't normally think about magnetics or just magnetostatics and things like that in terms of a ground and a voltage, really. But you do need to, when you think about this, you need to fix Vm somewhere in your system. Otherwise, there will be infinitely many solutions. And it doesn't there's an element at which it doesn't really matter that you've fixed it, because all these linear transformations are allowed, although it really should relate physically to your system. So before I give you an example of the magnetic fields, no currents, it's important to talk about the magnetic materials models. And this will also be true for the magnetic fields interface when I speak about that. COMSOL has in it, as you saw with Taylor, it has in it this ability to talk about all these different constitutive relations between the E field and the D field, or the B field and the H field. Now, there are a large amount of magnetic media in which this isn't linear. And not only is it not linear, but it demonstrates hysteresis, as this does here. And there are a variety of ways in which you can model either the entirety of a curve like this with the Giles-Atherton model, or just the linear part, or perhaps just one side, etc., with these different magnetic constitutive relations that are available in COMSOL. So you can, say, just use normal relative permeability. You can have well-defined magnetization. You can use a BH curve. You can define a BH curve, which is one side of one of these, or it's one quadrant of one of these, really. And you can import them from data. And there are tools available in COMSOL to clean up this import and make it acceptable to the conditions that COMSOL places upon these things. You have an effective BH curve, which allows you to use your BH curve in frequency-dependent studies, frequency domain studies, for example. Yeah, so this is actually quite an important thing to note if you want to do nonlinear magnetic material models. COMSOL is perfectly capable of modeling nonlinear magnetic materials in the presence of magnetic fields. You just need to be careful. You just need to make sure you pick the best constitutive relation for you. And you may want to provide it with experimental data. As I said, again, this is another thing where you can import a function, and you can import an interpolated function from data. So an example of the use of the magnetic field's no currents interface is a one-sided magnet. So this is one that's available on the application. I sort of go through it the way they go through it, which is at first you build a magnet, a standard magnet, and you look at the fields associated with that, and you have sort of a plate down here, which will be interesting later. And then you can adjust the internal properties of the magnet to be a Hallback array, which produces a one-sided magnet. You can see the magnetic flux density is essentially coming out of one side of the magnet there. This is also a good example of using nonlinear magnetic materials, because you have this plate under here, and it's in 3D, that's just a 2D slice of it, with which you can model a nonlinear magnetic material with a given BH curve. So when you go through this example, you go through and you create this one-sided magnet, and you look at both the magnetic field that comes out of it and it's called the differential relative permeability of the nonlinear plate. It's just a way to look at how the permeability is changing in the plate because of this nonlinear relation and the varying BH field around it. And you will also compare that to a linear plate as well. It's quite a nice example, actually. I think it illustrates the sort of thing which you might want to use, not just magnetic fields, no currents for, but also moving on to the full magnetic fields. So in this interface, you have generically non-zero B field and generically non-zero currents. And you solve this nearly complete set of Maxwell's equations in the A formulation, which is in terms of the magnetic vector potential A. So the magnetic vector potential is your dependent variable. The reason I say nearly complete is because there are a couple of reasons. One of the main reasons is that in time-dependent studies, the second time derivative of A is neglected. And it's neglected because those effects are generally very small in low-frequency studies. It is present in frequency-dependent studies because of because you just have this harmonic term, IHW. Yeah.
Is there any chance to simulate the sliding electrical contacts in 3D with the MF formulation?
So, sliding electrical.
Because that might be related with the second time.
So, not with MF. As I mentioned earlier, there's MEF. So MEF is sort of the most full variant, and in that you solve this sort of inherently ungauged variant of Maxwell's equations, and you solve for both A and V. V isn't quite the normal electric potential, but it's in terms of, you can write the electric field as the time derivative of A and the spatial derivative of V. So you solve for these two variants, and you can have sort of electric, that allows you to have sort of these more electrical properties in your study. So things like you can define a voltage across something as well as solve for magnetic fields in it.
It's going to be a time solution for it.
Yeah, that one you can solve in the time domain, and then that will include these second derivatives of the A coefficient. It'll include all these extra derivatives things. It's just you just have to be very careful with MEF, magnetic and electric fields, that you're setting up a well-posed problem, because it's very easy to accidentally set up one that has infinite solutions somewhere, or can't be solved somewhere, or won't converge. That tends to be why we recommend using things like MF if you can. MF is good for most sort of industrial applications, so things like magnetic fields in and around conducting media where you have a known current in that media, voltage or power inputs, and you're not interested in all these extra sort of smaller, I guess, capacitive effects between them and things like that. It's all done in terms of, you get this extra feature in the MF called the coil. And the coil is quite unique to MF, and it's the way that you drive current through MF, and it's designed to sort of model an electromagnetic coil in essence. But so magnetic fields, you solve for this magnetic vector potential, you get the B field and you get the A field as well from that, but you get the A field assuming that the gradient of V is 0. So there's an assumption there which you do sometimes need to be careful of. Most people, it's actually not a problem. Yeah, you have stationary steps, you have frequency domain steps, you have time-dependent steps, and they're all appropriate here this time. You also have this preset study type called coil current calculation, What that does is when you set up your coil as putting a current through, if you have sort of a numerical coil with an odd shape, it solves an electrostatics problem within the coil to work out how the current flows within the coil on itself. The coil is also interesting in that it has a defined voltage within it and things like that, which will be important later. Whereas voltage isn't generically defined. It's one of the lumped parameters that gets defined for the coil and allows you to calculate things like inductance in coils and so on. So the example of this will be this simple sort of E-core transformer, again, available on the website, available in the applications library. It's, again, 3D, time-dependent study, and the idea is that you've got two coils. One is a primary coil, which is excited with an external current source, well, external voltage source with a set current, via coupling to the electric circuits interface, which I will mention in a moment. You have a secondary coil, which isn't sort of, there's no electrical conduction between the first coil and the second coil. There's an insulator there, but there are induced currents, and you're looking at the induced currents as you might be interested in the transformer. You use a BH curve model to model the non-linear core material, and in this case, that's an example of the BH curve which you might input in and interpolate in order to get it. As I said, it's one quadrant of that, essentially one quadrant of that hysteresis curve. This allows you to calculate things like the magnetic flux density, the induced current and the voltage in the secondary coil, which is plotted there, and it allows you to look at losses, frequency average volumetric losses in the surrounding core. So that would then later relate to heating if you wanted to add that on, for example, or you can just look at it from the electric currents if you're not interested in how heat conducts through the material. So I mentioned the electric circuits interface then, and I'll briefly talk about it here as well, because it's a special interface in AC/DC. It is essentially a control interface. It allows you to model this a circuit with ideal components, and it allows you to couple your finite element model or your boundary element model or whatever in as a component of that circuit. It works by solving the system of ODEs for voltage and current across every circuit element. And when you couple in and out of it, you have these special coupling nodes, which say to a coil, it will pass a current, say, from the circuit to the coil, and that will excite the coil. And then the voltage is then calculated in the coil based upon everything that's happening in the finite element method, and that is passed back into the circuit model, which then solves it as part of the circuit model. It says stationary there, but you need to be very careful with stationary study steps in the circuit model. Generally, frequency domain and time dependent are the way to go. And you'll get
Can you just explain that again?
It's a bit.
So this is all happening within COMSOL.
This is all happening within COMSOL.
It's not that you can export a model that you can put into another SPICE system.
Yeah.
Or can you?
You can export the SPICE into. So you can export the SPICE interface.
So let's say we use something like
this is within
SPICE
COMSOL.
or some of these things to simulate our circuits.
Yeah.
Or cadence or one of these circuit simulators.
Yeah.
If we do something within the COMSOL, can you export then an equivalent circuit model back into an anti-SPICE?
I believe so, yes. You need to be a little bit careful because sometimes, so the circuit nodes which relate to the coupling aren't sort of normal SPICE nodes, if that makes sense. So you need to be a little bit careful. I think generally what people do is quite often they design a circuit elsewhere and import it into COMSOL and replace an element with the coupling to use the circuit to control the finite element model in a way.
Okay, so on that point, so if we've designed something like, some simple amplifier circuit or whatever, and there's a way to export that circuit and have it function within COMSOL, so that that amplifier circuit, if it's working by itself, but it couples into your
you add a node to your circuit, which is sort of like treating the finite element model as an element of the circuit.
Okay.
It's like sort of a little box with a question mark on it that takes in, say, a current and spits out a voltage, or takes in a voltage and spits out a current. Generally, that's how it works.
Just sorry, one more question.
Yeah.
In terms of the circuit, obviously the netlist gives you the connections.
Yes.
between the
Yeah.
circuits, but the SPICE system will need to have models for each.
Yeah.
element.
So.
Can you use very sophisticated models? I'm thinking of semiconductor devices,
I-
or is it relatively primitive models that?
So, the models that are available in COMSOL, it solves within COMSOL sort of on its own, in the sense that COMSOL takes in the netlist as this set of nodes, and it then solves everything all at once, with the according to the system of ODE. I can't remember which ones they are. The system of ODEs and that, and it assumes sort of like an ideal capacitors in the circuit and ideal resistors and things like that. You can include semiconductors because I believe the electric circuits interface can couple into the semiconductor module. But I haven't done that ever.
Suppose I don't want to model in COMSOL,
Yeah.
I just want to use the SPICE model that my manufacturer may have supplied me. Can I import a manufacturer's SPICE
You may
model?
be able. I'm not sure on that because I've never seen it done. We've never tried that ourselves. And yeah, you may be able to.
I mean, kind of related to that. Is it importing SPICE from somewhere? Or
No,
is it
it's
solely
importing.
ODEs?
It's importing the netlist, and it's got the ODEs built into
Right,
COMSOL.
so it's not a SPICE
yeah, it's not. Yeah, it's the wording there is a bit odd. It's not a direct. It's not directly importing a SPICE direct import. It's importing the netlist, and it's solving sort of as SPICE does, but because it has to solve it.
Matrix.
I know,
Yeah.
but if it was importing NG SPICE libraries,
Yeah.
it would be able to.
It's the libraries that would be able to.
Yeah, it's sort of. Yeah, and it has to solve this ODE in conjunction with the finite element model as well, because one of the inputs into the SPICE into the circuit, comes from the solution to the ODE, which itself takes an input from the circuit. Yeah, so that's one of the nicer things about that comes in the AC/DC model actually, and it can, as Taylor said, you can use the circuit interface to control in the RF module and the wave optics, etc. And I believe you can couple it into semiconductors as well. Essentially, anywhere that has a terminal or a coil, you should be able to couple the electric circuits into. Basically, anywhere that has one of these, because these as I'm about to show, these AC/DC modules actually appear everywhere, which is one of the reasons why it's so important to sort of hear about it. So we have key multiphysics couplings. You have electromagnetic heating. We've already gone through Joule heating and thermal expansion. It gets called induction heating when you do it with magnetic fields, but really it's the same sort of process. You just have your sort of time averaged in the frequency domain electric components to your heat transfer. We have a large set of pre-built multiphysics interfaces between electromagnetism and mechanics. So you have things like rotating machinery, which allows you to model electromechanical motors. We have things like piezoelectricity, as I mentioned, magnetostriction, etc., etc., etc. Those all pre-exist in COMSOL and are used quite regularly, actually. Elements of the AC/DC module will also make appearances in other physics modules. So, for example, in the plasma module and the semiconductor module couples to the electric currents interface, which comes from the AC/DC module. You don't necessarily need the AC/DC module to run it, but it is the same interface. In the MEMS module, which is for microscale sort of electromechanical systems, you get your electric currents in there again. And you have various things from structural mechanics sort of contained and on their own. You can also do coupling to CFD with magnetohydrodynamics. That better examples of that are something that's being actively worked on at COMSOL. There is one example of magnetohydrodynamics, but there are improved examples are coming. And of course, we have connections to the chemistry modules. It's the things like the electrostatics and the electric currents interface again are used in the corrosion module. They're used in electric deposition, electrochemistry, etc., etc. AC/DC ends up appearing everywhere, especially things like the electric currents and electric charges. So just before I go on and just talk to you a moment about further resources, it's worth saying this wasn't even a complete tour of AC/DC. I didn't have time to do any demos because it's so packed with stuff. As I spoke a moment about the MEF interface, there's also the MFH interface, which most of you will never touch with a barge pole. But it solves Maxwell's equations in the H formulation because that is appropriate for modeling superconductors. So the example I showed of CERN for their superconducting coils, they will have used MFH in that, for example. So if we move on, we've got further learning resources. I thought I'd show you a different slide to last time. Essentially, when you go to the website, that's what the Learning Center page looks like. And if you see everything, all of these resources are nicely grouped according to physics. And you can go and you can click low-frequency electromagnetism and you can search within that for examples. We, of course, have COMSOL support in the knowledge base. If you're struggling, there is a complete user's guide, which is essentially the complete documentation for the AC/DC module. It's very long and in-depth and possibly will not be necessary for all of you, but it is useful to go and see exactly how something's working. And finally, I'm going to mention it because I really like them. Walter, if you're ever doing modeling of the magnetic field interface, which is the last proper interface I spoke about, you're going to use coils. You are going to use coils. They are sort of inherent in the way things are done in that interface. Walter Fry, who's an applications engineer in the Boston office, has done a massive, over COVID, did a massive lecture series on how to model with coils properly. It's 20-hour-long episodes long. And it covers 2D modeling of coils, it covers electromagnetic heating, it covers how to calculate electromagnetic forces properly and all the pitfalls that are involved in there, and it does coils in 3D and proper meshing. And they're very easy to dip in and out of. So that's something else as well. If you just search COMSOL coils, he comes up. So that's important to know as well, because I find it very useful when I first started. I found it very useful when I first started. So what's next? So we finished the morning, essentially. We're now coming on to the lunch break, just after hopefully a quick Q&A, because I went on a bit too long. And in the afternoon, there'll be studies and solvers, and then application builder, digital twins, surrogate models, and then we'll end at about 3 o'clock.
Should we give everybody a clap?
But yeah, thanks for joining for the first of these afternoon sessions. This is going to be on studies and solvers, so just a bit of an introduction to the sort of options you have within the study node itself, and a few tips on how to deal with, well, how to speed up certain simulations, and also how to deal with more sort of challenging nonlinear problems. Okay, so in terms of COMSOL, a COMSOL model defines a series of physical equations which are based on the interfaces and boundary conditions you've included to define your problem. It then takes a numerical method, which is typically the finite element method, but there are others supported, so the boundary element method, which we touched upon within RF. And then it takes the mesh, and it generates you a sort of matrix equation that can then be solved using the solvers that COMSOL supports. So yeah, when you combine them together and you get your system of equations, you get a certain degrees of freedom, we say. So the sort of size of the matrix that you're trying to invert to get the solution. And that number can be very large. It can be above 1 million for larger, well, larger meshes, or more complex physical systems with lots of different dependent variables. But ultimately, it's your study node that defines how you solve that system of equations. So COMSOL automatically generates a solver configuration for you based on the sort of size of your system. If it's a larger size, it might start to use iterative solvers, which are a bit more efficient but can be less stable. Whereas if it's smaller, it'll use a direct solver, which takes a lot more RAM typically, but is more stable. So yeah, it'll make choices and even give you some alternates that you can have a look at in the solver configuration that you might consider switching to by right-clicking and pressing enable. But yeah, so it'll try and give you a system that will solve your problem. And the requirements of the solver are to gain a solution, so that's solver stability. So that's mostly influenced by your choice of solver, but also by the quality of your mesh elements. So if you're having convergence issues, one thing to consider is whether you're meshing sufficiently fine enough in all areas of the system, especially if there's areas where your solution might be varying quite quickly. The other priority is to try and get an accurate solution. It's going to sort of solve the system within a given tolerance. So if you want a greater sort of local accuracy, then you should increase the mesh, which obviously there's a counterpart to that starts to increase the sort of RAM usage and the time that it'll take to solve your model. So there's sort of a payoff there. And then it tries to compromise between speed and accuracy. So too many elements will take too long, but too few gives you large errors. But there are some things that we can do about that beyond the sort of solver configurations, which we'll talk about here. Okay, so in terms of the options within the study node, you can, well, if we go left to right, there's the option to show the default solver. So this is sort of underneath your study steps. This is the solver configurations you'll see. This is where all the more detailed settings about what types of solvers are being used, whether it's iterative or direct, or how many iterations. You typically don't need to modify these, but if you want to, you can hit Show Default Solver. It'll generate that solver sequence for you so that you can look at it before you hit compute and try to solve the model. And you can also show the default plots that are going to be generated if you want to modify them beforehand, or even reset the default plots. You can then add a variety of different study steps. So typically we've been doing stationary and frequency domain so far, but there are other types. There's time dependent. If you're combining different sort of types of physics, you might do a frequency stationary or frequency transient as well. Then there's a range of parametric analysis. So when you've defined and parameterized your model, you can then solve for a range of different parameter choices and see how the value of that parameter affects your results to try and do maybe some basic optimization, or just test a few different design choices. And you can do something similar as well. If you've implemented a function as you've defined a function to represent some sort of input, say a flow velocity or a field, then you can sweep through a variety of choices for that function as well, and a variety of choices for the materials applied to your domains if you want to see how that affects your solution. Then combined solution, this is mainly for time-dependent problems, so sometimes it makes sense to split a time-dependent study up into two different study steps. If there's a change in the sort of dynamics of the system, say, you can switch it on in the second study step, and then you often want to combine those two solution data sets together so you can visualize the full picture. So that's combined solutions. And then we have quite a few advanced analysis tools as well if you're getting into things like optimization or even uncertain quantification, sort of putting limits on, there might be errors in some of your inputs and seeing how that affects things. And surrogate models, which we'll talk about in the last session, which is a new feature to 6.2. And then also there's some option for parallelization as well. Okay, so this is the study step. The things that you can select here, you can choose what physics you want to solve. You don't necessarily have to solve all your physics at the same time. There are cases where it makes sense to split the problem up into multiple different study steps, which we'll talk about later, especially if you're dealing with a one-way coupled system. You can also, if you have multiple meshes that you've generated, you can generate multiple meshes, especially if you're trying to see what the most efficient, or if testing out different approaches. You can choose which mesh to use, and you can set the form of the equation solved. I mean, this is typically done by default by the choice of, so if you have a stationary study step, it's going to solve the stationary form of your equations. Okay. There's also the option to enable or disable a specific physics or even a specific feature. So, I don't know, is it in there? So you see just above the list of physics is this tick box, modify model configuration for study step. If you tick that, you can, as you sort of did before, you can disable physics. So if you want to just solve for, in this case, the laminar flow and have a look at that before you're going on to looking at the full non-isothermal flow simulation. But you can also disable specific features. So you could solve this flow problem, for example, with and without this interior wall. So you could right-click it and disable, have a look at what the unimpeded flow looks like, and then enable the interior wall and have a look what the impeded flow looks like, just to sort of have that difference there. So that's one example. It also can be used in that time-dependent example. If you have a source that only gets switched on at a certain time, then maybe you only enable it in a certain study step. Okay, yeah, and you can, there's a wide range of study steps available. Some of these are sort of physics dependent, things like ray tracing or others, or the Schrodinger's Poisson. And you can add multiple to a given study to make them more complex. So I'll talk a bit about this. This sort of plays into how you can sometimes speed up your simulations. If you split them up into multiple different study steps where you solve different physics, one-way coupled, that can be a lot quicker. Because of what you're essentially doing is, if you solve the full coupled problem in one go, it's a larger matrix system, and it sort of, the cost to you goes by the square of the degrees of freedom. So if you split it into two smaller problems, then it's a lot quicker. So you could do this in one study. The advantage of this is that the variables between, so for an example, say it's a sort of current problem where you're doing the resistive heating. The variables you might need in the heating problem, which would be the loss variables from the electric currents interface and the sort of electric current information, that will be automatically passed from the first step, if you were to solve electric currents in step 1, to step 2, where you could then solve heat transfer. So that's sort of automatically done if they're in the same study. You could break them up into two different studies. So the advantage of this is that you then don't have to solve them together. So you could, you could compute the electric current problem, and then that's fixed. And then you could spend a lot of time trialing different setups of the heat transfer problem. And you'd have that electric current problem sort of solved, and you could access that solution without rerunning it. You'd just be rerunning the heat transfer. So it gives you a bit more flexibility. But you do have to manually tell it where to get the information for the sort of resistive heat. So you go, I'll show you this in the software in a second. You sort of tell it to take the variables it's not solving for from a given solution, and you'd point it towards a given study. And there's also the sort of more complicated options where you do study references, so you could reference multiple different studies in a third study, but it doesn't come up as often. Yeah, so this is the example I was talking about there. So you would solve study 1, stationary step that solves for your electric currents, so you get that potential difference information and currents. And then in the second study, where you have heat transfer in solids, you solve that, and if you don't pass it any extra information, it'll give you an error message being like, I don't know what the losses are here. But if you go to variables not solved for and choose user-controlled solution, study 1, it'll take it from that study. So the variables solved for in this example, if you're solving for heat transfer, is the temperature, and the variables not solved for are the voltage and anything defined from it. This also relates to if you're doing a time-dependent problem. You see above the variables not solved for. There's also the initial values of variables solved for. So sometimes time-dependent problems, you can get an inconsistent initial value. So sometimes you might want to do an initial stationary study that solves for your initial values, and then pass that to the time-dependent study, and then solve from there the time evolution. So similarly there, you could do that in two different studies. And if that's the case, then you need to tell it where to take its initial values from. If it was all in one study, then it'd be automatic. But if not, then you need to do this. Okay, so you can see the sort of effect this can have in terms of speeding up your models with this example here, the laminar static mixer. So I'll open it up in COMSOL. Okay, so just to explain this model a little bit, it's a 3D model. We're solving for two physics interfaces. So we have laminar flow. You can see this is a tube with some. If you see these exclusions here, these represent walls that are sort of curved around. So it makes a sort of mixing as flow passes through it. It'll mix that flow. We then also have a transport of diluted species, which defines an initial inflow of concentration of this sort of arbitrary species C0. And you see here it's got a step function. So this is what this means. Well, the step function is defined here. It'll just mean that there's concentration on one side, there's high concentration on one side and nothing on the other. So it's completely unmixed at the start. So we define an inflow, and then it can outflow over here. So this is a multiphysics problem, so that how the concentration sort of is transported is very dependent on the fluid flow, but not vice versa. So this is the exact example I think Joseph came before. We're assuming that whatever concentration this is, it's not sufficiently concentrated to affect any fluid behavior. It's not going to make it more viscous. So the flow affects how it's transported, but the transport doesn't affect the fluid flow itself. So this is one-way coupled. And in the in the laminar flow, you can see we define an initial velocity and then a pressure of 0, and this will give us our sort of fluid velocity information. And that's the multiphysics coupling. So yeah, we could solve this as one problem in a single study step here, but this is, well, it's possible, but it'll take a lot more time. What did it say? Oh yeah, there we go. So you can see to solve it in this way, on a different computer that was better than this laptop, it took 5 minutes, but if you split it apart, it's far quicker, as we'll see in a second. So if I add a study, oh, I should show the results as well, just so you can see them. So you see the velocity profile here. This is a streamline plot, so you get these sort of spaghettis that follow the fluid velocity. You can see how it sort of mixes around, the pressure, and probably the concentration surface is good to see. So you can see that it's completely split on the inflow, but by the time it gets to the outflow, it's quite evenly mixed. So yeah, so we should be able to achieve the same results, and basically we're solving the same problem, but a lot more efficiently by using another study. So I'm going to add a study with a stationary step, and then add a second stationary step. So in this one, I'm going to solve the laminar flow, and in the second, just the transport of diluted species. And because this is in a single study, the information is going to be automatically passed from one study to the other, one study step to the other. So yeah, let's have a go at solving that. It should be pretty quick. But feel free to ask any questions if you want while it sort of just solves in the background. Okay. Oh, well, I can look at the convergence part, actually. I think it's probably already solved the first bit. Yeah. So you can see it's now solving two problems. So this is outputting 2 different degrees of freedom for each problem because it's solving 2 small matrices. Let's have a look at this convergence part. It's getting there. Let's have a look at the progress. 94%. So yeah, this will be done in a second. Okay, so yeah, we've generated some results. So the default results here are they've generated slightly different plots, but I guess the key one was the concentration surface. And you can see, we can see the exact same behavior. We have this sort of initial split, and you can see this is coming from study 2 that we just solved, and after it gets mixed. So we've got the same results, but this took 45 seconds on a worse computer. So you can see, if you have this sort of one-way coupling, it's well worth exploiting it. And then just in case it is useful, because it might be that you sort of are modifying the transport a lot more than you are the laminar flow, you're sort of playing around with the concentrations. If you wanted to preserve the sort of laminar flow in its own study, you would just give it its own study, stationary, solve laminar flow. And then again, in a second study, but now a sort of totally separate study, you'd solve transport, and you just have to go to the bottom and tell it that the values of variables it's not solving for that it might need are user controlled from a solution. And in this case, I'll tell it study 3. So now I can solve them sort of independently. Just I can compute that. The laminar flow, which I think is just a few seconds. Yeah, so I got the fluid flow results. And then I can pass those results to study 4 and get my transport results, which are the sort of key ones for us. So this, I mean, it should be at the exact same time in terms of if you added them both together, but just gives you greater flexibility. So I think the second study was slightly slower. Okay, let's get that. Okay, yeah, so again, we see some streamlines here. If I go to concentration surface, you can see this is coming from study 4, and it's the exact same results again, which is what we'd expect. Another thing that this enables you to do is, in both these second approaches, now that they're different, they're not being solved in the same matrix equation, we could have also used a different mesh on each, because sort of CFD problems tend to need a coarser mesh, because the sort of flow profiles are quite complex to resolve. Oh, you had a question?
Okay, sorry.
Yeah, sure.
Any of the studies, is there any of the studies that it's possible for you to recover each of the components at the outlets, like recovering it individually?
Recover what individually, sorry?
Like getting each of those components after feeding it in at the outlet, like recovering it individually.
Oh, well, like the actual numerical value or something?
Yeah, yeah.
Oh, yeah, you can do that. So if you want to get not just sort of visualizations like this, you want to get actual numbers out of the result, out of the simulation, where you go to derive values essentially. So you can, if it's a global quantity, something that doesn't relate to space, you could choose that. But if it's sort of like a concentration that is fixed to a particular coordinate, you would use a point evaluation, and you could choose a point and evaluate something here. Let's have a look. Concentration, why not? So then that'll evaluate down to oh, it's probably because it's at the walls. Annoyingly, this is one of the things, because you don't want to really use the points on the geometry, so you want to use a point internal. So what you do then is you define a cut point. So that allows you to define some coordinates, and then you can evaluate the value there. And that is also somehow on a boundary. Okay, so let's shift it by -1. There we go. So, I mean, obviously, you might prefer it to be on that outlet. So if you just worked out the coordinates of that outlet, you could do this. But for ease's sake, I'm going to use this point. So now if I, instead of using, so this cut point points to a data set. So it's coming from the first study, but they all have the same results, so it doesn't matter. Now I could point to the cut point itself, and then I don't need to choose a point. Oh, it just does it. Maybe I'm using the wrong variable. I don't use species C. Okay, this might be what I want. There we go. That's good. Yeah, so that would be how you do it. Cool. Okay, so I think that was everything, wasn't it? I think so. Those are the ways you can speed up one-way coupled problems.
Sorry, with that, is there a way to stepwise switch between the flow and concentration, flow and concentration, if you wanted to do other things to the simulation? So, because it's rather than, I can't think of an example why you need to do this now, but I can imagine it would exist. Where if you're doing a sort of time-dependent study,
yeah,
and you want to solve them separately, but you don't want to solve all the time of the laminar flow and then all the time of the concentration. Can you stepwise
Yeah, I think you should be able.
Into this, can you do that?
I think you might just need to use multiple time-dependent study sets, I guess. But in a couple of problems, yeah. I think, yeah, if you use multiple, that should be possible in some way. Okay, so yeah, let's go back to the slides. Okay, so yeah, the other thing we were going to talk about were sort of more difficult to solve non-linear problems. So linear problems are the nice ones that solve very easily. So the properties are that applying a zero load results in zero displacement. If you shift the sign of the load, you only shift the sign of the displacement. And there's a linear relationship, basically. So this is good. There are areas of physics like RF and acoustics, some areas of acoustics where everything is nice and linear and everything solves very quickly. But there are cases where things start to become nonlinear. So if you have constant material properties and applied loading, then you're in the linear regime, and that's good. But if you have things like where we said there's two-way coupling, if you have material properties that depend on the solution, or if the loads, and here loads could be anything from like a structural load to an incoming velocity or an electric field, if they depend on solution, that's even more nonlinear. And if you have combinations of the two, then you can become even more outrageously nonlinear. And this just becomes harder and harder to solve. So, like I said, there are some inherently linear physics interfaces like electromagnetism, except for the sort of magnetic behaviors that Joseph was talking about with the BH curves and everything like that. Acoustics is a big area that's linear, elastic solid mechanics, and heat transfer. So the techniques here won't be most applicable there. But we get onto things like fluid flow, where the Navier-Stokes equation is always nonlinear, chemical reactions, sort of more complicated nonlinear solid mechanics a lot of the times becomes quite strongly nonlinear. And if you're including sort of radiation or temperature-dependent properties, heat transfer can become as well. Then it's possible that you start to have convergence issues. And we'll talk about one way to sort of, or a couple of ways, or two ways to try and tackle that. But before we do that, we'll just talk about how it is that COMSOL is solving these problems with this example. So in the case of a spring attached to a fixed wall with a given force, we can try and solve for the displacement. Yeah, and we know that this elastic spring should obey Hooke's law. And the best way to solve that in COMSOL's sort of formulation in a COMSOL way is to represent the law, this sort of equation, as a functional. So we shift everything to the one side, and then we try and find the minimum. We try and find the value of u at which f of u becomes 0. So we're trying to find the root. And the way that we do that is we use Newton-Raphson method. So we start at some initial point u0. So this is the initial value guess that we've been sort of ignoring so far. We evaluate the functional, the residual at that point. So we put in our guess and see what we get out. Then we evaluate the derivative. And we update our new guess based on that. So this is called the Newton-Raphson method. And if it's linear, then this is guaranteed to converge automatically. All you need is your initial guess of whatever, and it's going to get to your answer. So that's nice, but things aren't always linear. So in the case where we have a non-linear problem, things become a bit more complicated. So if we had some exotic stiffness constant for spring constant for the spring that was now related to the displacement, what would happen would be that this first sort of iteration, we'd have our initial guess, which wouldn't be right. And then when we update, we'd also not have found the solution. But what we can do is we can just carry on taking iterations of the Newton-Raphson method, and it should follow the gradient towards the root. So we keep on taking iterations until we get to a point where the sort of residual, the difference from our solution, becomes small enough that it's within our tolerance. So we're happy enough to take that as our solution. And we can evaluate the sort of tolerance in a few different ways, whether by how different the solution is going or how the residual is changing. But near the root, the Newton-Raphson method should converge quite fastly. But the issue that we can have is it's possible that in our solution space, we're outside what's called the radius of convergence. So because it follows the sort of gradient of the solution curve here, which is 1D in this case, but higher dimensions, if it's outside of a certain radius, then following the slope is actually taking it away from the solution and it'll diverge rather than converge. So that means that our initial value, our initial guess for the solution is now quite important. So we want our initial guess to be as close to the actual solution as possible, which is where this sort of technique comes in. We try to force the problem to be one where we know sort of the solution. So yeah, these are the ways that nonlinear solvers can fail. You can be outside the radius of convergence, which just means that you are going to go away from the solution rather than towards it. Or it can be even an ill-posed problem. The sort of combination of boundary conditions might not result in an actual solution. So there's not much you can do about that, although it might tell you something about a breaking point in the system. But if you're in this area where you're just outside the radius of convergence, what we do is we sort of modify the problem we're solving. If we apply no load to the system, if there is no fluid flow, or if there is no applied field or anything, no matter how sort of nonlinear the problem is, we expect the system to be unperturbed. So if we apply a very small load, then we should be closer to the root itself. So we solve this initial problem where the load has been reduced, and we should converge using the Newton-Raphson method, hopefully. And then we take that solution as the initial value, the initial solution for another attempt where we increase the load ramp. So we've increased the load, but we now hopefully have a better initial guess. And so we follow this path on and on. And if we've sort of appropriately chosen the sort of initial load sizes and the gaps between them, we should then be able to converge on a solution that was previously quite difficult to converge on. So one way to set up a load ramp that we typically recommend is using an auxiliary sweep. So this automatically includes this feature that the solution from your first point in the sweep will be used as the initial guess for the next computation. So if we add a sweep there where we sweep over the load, then it should give us the behavior we want. Okay. So you can see an example of this with one of our online examples. So if I open this up, this is called the micro mirror. Okay. So this is this is a metallic mirror here. It's got sort of an aluminium legs and a structural steel body, and it's got this initial stress and strain placed on the legs that's sort of anisotropic, given by this sigma pre, so you can see here, which should give this twisting effect. And because this is, well, if we solve for a sigma pre like 20 gigapascals, which is a very high force, we'll get an extremely, well, we should get an extremely exaggerated deformation, which is quite a nonlinear solution. So it'll struggle to converge on it. So we'll give it a go the standard way. So we've got our model set up, we've got a mesh, and let's just check that this is switched off. It is. So if we try and compute now, you'll see it's having a think about it. If we go to the convergence plot, what you start to see is the error starts to jump around and doesn't quite get there. So the default is that COMSOL gives itself 25 iterations of the Newton-Raphson method before it gives up and says it's not converged. So there are cases, I mean, this was making some progress where you could actually just go into your solver configuration. You can see this is where all this information is. I've mentioned this before, but underneath the stationary step, or whatever your study step is, you have your solver configurations. This is what's actually defining the solvers used. You can see it's using a direct solver. And in the fully coupled determination, you can set here the number of iterations. So if it's a case where your problem just fails converging, it can be worth just adding some extra iterations. That's one way you can tackle this. There's advice and knowledge bases about some techniques you can use to try and change some of these settings. Sometimes adding extra damping can help make the model more stable. In this case, the best way to sort of fix convergence is to use a load ramp. So we've parameterized our sigma pre, which is the load. So what we can do is go to our stationary study, go to study extensions, choose auxiliary sweep, and then select sigma pre. So I'm going to change the unit that I'm specifying here to gigapascals, and then choose a series of smaller loads that should give us a sort of a ramp path that helps. Okay, so don't want to make any too big a jump. Okay, so hopefully that will help. So yeah, we are now solving, I guess, 6 problems instead of 1, but because hopefully each is going to converge a lot quicker, it should be fine. And you won't see much of a speed up because some of these are solving in just like 1 iteration. So it's very quick. So you can see we've solved for some of the low ones. Okay, there it is. But yeah, so you can see we've got this more extreme solution. You can see even with the load ramp, it wasn't the smoothest convergence ever here, but it did get to the solution. And then for these very small loads, it was pretty much instantaneous. But yeah, so we get the ultimate solution that we were hoping for just by solving multiple versions. And you can see as you go through, the solution is becoming more and more sort of extreme and far away from our initial value, which was sort of 0 displacement. Okay. So another technique which is very similar, it's sort of the converse of this, is viscosity ramping. So this tends to be in fluid flow. You could use it in other areas of physics, I guess, if the nonlinearity is very closely tied to a given material property. So in this example, the idea is that it can be very hard to converge very turbulent flows. So what you can do is you can add an extra parameter called ramp, and then use that to modify your viscosity of your fluid. So if you set a ramp to an initially very small value, the viscosity of the fluid is then much lower. It's going to be a lot less turbulent and may even be laminar. So you'll be able to easily solve it at first, and then you slowly ramp up the level of turbulence, and you should be able to get to the full turbulent solution. If you just tried it straight out, you might not be able to. So yeah, that's a technique that gets used a lot in CFD. Okay, all right. Well, I did this. Okay, so yeah, I think that was everything I was going to show. I can't remember. I've lost sense of time. Am I early?
You're about 10 minutes early. Yeah, that's fine.
That's fine. Okay. But yeah, are there any questions about anything, studies and solvers? Go ahead.
So that one was a large deformation analysis. What formulation is that based on?
What formulation? I'm not a structural guy really. Let's have a look. I think it is still just treating as a linear elastic material. Just with a very, but it will be it's including geometric nonlinearity in the solution as well. But yeah, I'm not.
Is it update the Lagrangian or something like that?
It's when you solve structural mechanics, especially if you tick this include geometric nonlinearity, all the equations are sort of formulated on it's a material frame, so everything deforms as the material deforms, so it's including all those sort of effects, which I think is related to that Lagrangian thing that you mentioned, but I'm not an expert in that area. But yeah, any other questions? Oh yeah, sorry, go ahead.
Sorry to ask again. I'm wondering if you've tried model, like, so that the model could learn from results generated from all this you're testing, so that in the future, someone will not need to run through this.
Yeah, I think that's
feeding in the future and it gives straight.
You can do sort of machine learning techniques. That's going to be the last talk actually after this one. But yeah, it's a new surrogate model feature. So if you solve a model for a large set of parameter choices, then you can train a surrogate model on the solutions of that. And given enough training time, and assuming you choose, I mean, it's typically uses a neural network. Given that you've tuned that properly, it should give you a surrogate model function or series of functions that replicates the solutions you want without having to solve the model. So it does. I mean, it then replaces the model, but first you have to solve the model and train the surrogate model. So we typically envision it might be useful for apps if you're handing it over to a collaborator, because it speeds up the solution time for them. Instead of having to solve the model, they just evaluate the surrogate function at the sort of parameter choice they want. So that's sort of related, I think. So you want the fluid to drive the impeller, or the impeller's already spinning?
The impeller's spinning. So would it be like a spinning mesh?
We have moving mesh, so it could be a moving mesh functionality. I know we have like a whole mixer module and everything, but again, I've not done it. I do imagine it's possible, and because there's a mixer module, there'll probably be a lot of examples online, but it's not something I've ever particularly done myself. So. I'm not sure I can offer too much useful advice.
Yeah, again, I don't really know specifics, but we do have a mixer module which is designed specifically for that sort of thing. Yeah. So you can have an impeller that drives the mixing, or you can have the other way around as well. And there's a lot. It also includes like geometries as well, with impellers and stuff like that.
I wonder if it's worth
trying. I don't know the details of how to set it up.
Yeah. Yeah, so you see there's the mixer module here. I don't know what would be a useful one to open. Let's have a look at this. Oh, the K. Yeah. So yeah, this is the sort of area I'd suggest you have a look at. But yeah, so it's using a moving mesh and a rotating domain. So we have moving mesh functionality, so it seems like that's probably something you're going to need to use. Yeah, no problem. But yeah, any other questions?
All right, in that case, I guess we take a quick break.
Take a break, yeah.
Yeah, about 5 minutes, and we'll start the next one at 4:15. Let me trust you.
Well, there's that.
I think that's probably what it is. Yeah. True. also some of them will come. When? Yeah, I do, but it might be good to go on the website. I do. Oh, one sec, yeah, one sec. I'll have a look.
I think there is a button. Sorry. What's the other? While he's looking that up, no, you can edit the example. The example model is just a model that's been made, right? So you can edit stuff and the other stuff and add to it. Right? As if someone just sent you a model. It's the complete model.
The whole idea of my research is to use exercise support
Tell you what, we have got permanent magnet motors in 3D.
Yeah, so there is a, yeah, so that's,
Oh, we can actually go. Oh, yeah. But also, I can send this stuff to you if you like. Yeah, I'll get you a business card.
yeah, I don't know, because I'm not an expert.
Just drop me an email and let me know what it is. Remind me of who you've got. And then I can send this stuff over to you. Because it looks like we've got a few different models, yeah. So, you at Newcastle? There are a couple of licenses available that I'm aware of. I think someone actually bought a license earlier this year and left, so that one might just be floating around.
Yes, I know.
Yeah. Yeah, if they've left and the license holder's happy with it, you can just switch over to a different person's name. So yeah, again, you can just email me about that.
Is it still active?
I think we've emailed you before about that.
Possibly.
They've had some talks with
Well, it wouldn't be me that deals with it, but it might have. So that's why I might not see it. But you can send that to me. No worries. Cheers. Oh yeah. Well, I'll send it later. But there's a few on here. Permanent magnet exclusion, efficiency map, counter diagram. I'll send it all on there. Yeah. Oh, right, yeah.
Yeah, that's one thread. That's one thread times sphere to teach how to use reduce field point. It's just like sphere of different backgrounds. Those steps, one, two, like 8 steps.
Quite fascinating.
Yeah, you can crack on now,
I think there's a few people that are still out, but I think it's
this, well, we're supposed to finish it. Oh, about 10 cars, yeah.
Oh, crack on.
I don't think the application library is available to us.
Okay. It might just be that you need to download it. I mean, everything that's there is also on the website. If you search the website, you can find all of it.
most of the time they have tutorials for it as well. It's like for COMSOL, you don't have to like go when you're on the overlaps, right? It automatically understands.
Yeah, it automatically calculates the overlaps and creates domains for you.
That's so smart because for like answers you have to put it on it.
Alright.
Yeah, it's like so if I want to include like impeller, I
Mhm.
just create the tube of fluid and do.
Yeah, you don't need the walls. It's like the space inside the tube.
Thank you so much.
Okay, thanks for that. Cheers. Okay. So yeah, I'll start the final session of the day. This is going to be on the use of the application builder, and in particular, how we can use one of our new features, which is it's available in 6.2. Someone mentioned to me that you might only have 6.1 actually, but I guess as soon as you have 6.2, you'll have.
Newcastle should have 6.2.
Don't know if it's one of those things where it's not being rolled out because of IT.
Yeah, I don't know. Maybe they have a weird thing where people you can still download older versions.
Yeah.
Have the newest ones.
And it's about to
It might be an IT thing.
Yeah.
But they should be available.
And 6.3 is about to come out, so
Yeah, 6.3
if you're a version behind, you'll be about to have 6.2. But anyway, so if you find you don't have it, it could be a version issue. Okay, so just in terms of first introducing apps and mentioning the different areas, so we've mainly been using and talking about the model builder, which is where we actually build the models and do the simulations and find our results. But we also have these other areas that we have touched upon. The application builder, I think Joseph mentioned, is for building simulation apps. So this is simplified versions of the full model that only contain the sort of inputs and outputs that you decide to include, and you can design your own user interface as well. And they're typically meant for using with collaborators who don't want to sort of deal with all the sort of detail that maybe you've gone through. They just want to be able to change some inputs and see how that affects the results. So that's the application builder. You can build apps there. We also have the model manager. Again, that won't be the focus of this session really, but it just allows you to more efficiently do version control. So you can save just the differences between different models rather than saving each individual model. It saves a bit of memory. And there's also a lot of tools for sort of tagging and searching for different versions. Okay, so yeah, we've got very used to the model builder, which has this user interface here, has every single feature that you are modifying included in it, and has your graphics window. When we go to the application builder, we're dealing about, well, to go there, first of all, we use this icon at the top, application builder. You can also see the button for the model manager if you want to go there. But when we do that, we then are in a space where we can design and test apps. So you can create the user interface by creating a series of forms and objects that relate to your inputs and design exactly how you want it to look. And then you can test it to see how it would actually run for the user. So you can see the finished example here. So from the battery pack, maybe better to go there. So you can see the full version of the battery pack had all these equations. It had a variety of different physics interfaces. This even had multiple components. So like passing this off to someone, all of this detail might be a bit overwhelming. When we go back to the app, what you have is just a few design choices related to the battery pack, some conditions, some operating conditions, and then a few buttons at the top which allow them to either sort of compute various parameters or update the design or compute their new version of the model. So it allows them to do some modeling but not have to deal with everything if they don't want to. So yeah, these are the differences. That's how the sort of contrast between the two. So it's a user interface built on top of the full embedded model. It can include inputs and outputs, and you can even include in sort of documentation and report generation if they want to just be able to click a button and automatically generate all the standard sort of figures of merits or outputs that they're interested in. And any sort of model builder feature can be included and controlled within the app. You just have to sort of choose what you want to include for them. So that's apps, and they can be obviously useful collaborators or even, well, certain commercial people, they're just building them to offload to another, to sell them essentially, so they can be used by another company who just wants to be able to predict how their system is going to work. And in terms of distributing them, there are a few different things to touch on. So COMSOL Multiphysics allows you to build apps, but to actually distribute them, you either need COMSOL compiler or COMSOL server. So COMSOL compiler allows you to compile an app as an executable file that you can then run freely on any computer. You can just hand it off to them and they can run it. Whereas COMSOL server allows you to host and administrate your apps through a web interface. So they can log into a given URL that you provide them and get to the app that they want to work with. So it's two different options, but there are extra products that you would require. And now to mention surrogate models, which we think pair quite nicely with apps. This is quite a new and powerful functionality we've included with version 6.2. It allows you to create a simpler, computationally less expensive model from your full finite element model, which approximates the behavior of the more complex, computationally intensive model. So it's accessible through definitions and solvers. It's not linked to any specific module. And there's specific studies available for generating the data that the surrogate model is trained on, which use design of experiments techniques. And the idea is that when you have the surrogate model, then the app becomes a lot quicker. Rather than having to compute again, which could take, 10, 15 minutes, or if it's a very complicated CFD problem, maybe it's hours, although you would have to train it first. So if you're trying to train something that took several hours and do thousands of iterations, it could be difficult. But the idea is it speeds it up for them. So for them, it could potentially become instantaneous, which they might want, but especially as they get divorced from the modeling side of it, and it's just a tool in front of them, they might want it to be instantaneous. They don't really want to wait for a system of equations to be solved. So it's a lot faster and should enhance the sort of user experience and should hopefully improve these apps. So the sort of workflow we imagine is that you create your full model, which should be a working model that accurately represents your system and can be solved for a range of different parameter choices to get accurate results. You then solve that model using design of experiments for a wide range in your parameter space to get a design data table. And then you train the surrogate model based on that data table to give the surrogate model, which is essentially a function, a multi-dimensional function that you can just plug into the parameters and it spits out the outputs that you specified. So it's the training, there's a certain amount of time for training, but the big sort of time sink is generating the data table, because you might, to get a sort of wide parameter range and an accurate surrogate model, you might need a couple of thousand solution points, which is also why there's a design of experiments thing that goes into it. We'll talk about that a little bit more later. But there's also the option, if you have a third-party tool or you just have experimental data, you can skip the model part of it, and you can just use COMSOL to train the surrogate model based on that data. So you import essentially a text file with your parameter space, and then use the sort of neural network aspects to then train on that. So that's another option. And you can then, integrate it with an app if you want. Okay, so surrogate model training study. So this is where we go from the model to a series of data points. So we tell it the outputs we want. So here, this is the tubular reactor that I'm going to be showing in a bit. In this case, the sort of outputs we're interested in are the temperature of this reactor system. So there's some concentration that goes in, there's a chemical reaction, and we're interested in how much the chemical reaction is happening and what's the temperature that occurs because of the heat that's released. So we want to output this variable here, which is this is a point probe, so it's at a certain point it's taking the value of the temperature. And at another point, we're taking the conversion rate of the chemical species. Then you give it the input parameters. So this is the parameter space, so what you want to be able to vary and choose from. So in this case, because we want a full 3D prediction, we've got R0 and Z0, which are coordinates. So we're sampling not just sort of input material properties, but
points in the coordinate space. So when it goes through and sort of solves individual iterations, it's testing the temperature and the conversion rate at different points in space to try and get a full 3D picture of how the temperature profile looks. And then it's also varying things like the activation energy, the thermal, I think, conductivity potentially, and the heat of reaction. But we'll talk about that more when I've got the model actually open. So these are the things, defines our parameter space. You can see we specify how these can vary as well. So these are sort of tied to the dimensions of the actual tube, and then these are just the reasonable range that we're considering. And then the sort of design of experiments aspect of it is that instead of, the few choices you could do is you could do a standard sweep where you just do a point at, say, if we've done 4,000 points. So you break each of these into 4,000 points, and then you do every single combination, which obviously the issue with that is you get a huge amount of combinations that is going to take you an incredibly long time to solve for, to the point where there's no point. The other option is randomized, just choosing random points in the parameter space, which reduces the amount, but you do have the issue that there might, because it's random, just be a point in the parameter space that's not at all well probed, and then your surrogate model is going to fail in that region. So what we do is we use, so I think it's called a Latin hypercube technique, where you break each of them into sort of 4,000 elements, and then each parameter gets sampled in that each space once. It's a bit hard to describe for multidimensional, but if it's just a cube, if it's just a square, then you would say you only have, if you had two parameters which would form a square, you only have one in each row and column. So you end up getting a decent representation of the entire parameter space, but without having to use as many iterations. So anyway, so this is what you solve and generates all your data. This gives you your design table, which you're going to solve the surrogate model on. And then you do the training. Okay, so when you've solved that, you'll get a design data table that looks like this. It's just a series of the first 5 columns being the sort of input parameters, so the choices we've made, and then the resulting outputs, which would be the temperature and conversion at these coordinates. And the alternate way is that you could import a text file as well, and the number of points is related to that input points. So if you say 4,000 input points, because of the sort of hypercube, Latin hypercube method, you end up having to solve 4,000 rather than 4,000 to the power of 5 or something. So it's a sort of sparse parametric sweep, as it says here. And because this is it's a sort of parameter sweep, it's very parallelizable. So if you have cluster computing, you can speed up this process a lot by sending different iterations of the parameter sweep to the different clusters, and then solving them at a parallel point, at a parallel time, which can speed up things a lot. Okay, so when you have that data, we then have a few functions that you can use to try and represent the design table data. So these are sort of multi-dimensional interpolation functions. So we have the interpolation function, but you can only use 3 arguments, whereas in this we have, say, I think it's 5 inputs. So the interpolation wouldn't do. You need one of these more complicated functions. So the one that was added in 6.2, which was more sort of aimed towards this surrogate model thing, is the deep neural network. So you're sort of using a neural network type machine learning technique. But we also have the polynomial chaos expansion and Gaussian process, which we had for uncertainty quantification before, and also are tied to the uncertainty quantification module. So if you try to use them, then you have to have that module. Whereas the deep neural network is, I think, available in the COMSOL Multiphysics, so available to everyone who's using COMSOL. So you sort of define your neural network, the series of layers and the series of nodes, and then the training will essentially just try to optimize the weights that go into that network in order to minimize the error of the surrogate function. Yeah, so the deep neural network is the most general purpose, and it can handle data tables with far more rows, so it can go up to millions, and is included in the base package. The others are available, but they are tied to, as I said, quantification, and can deal with fewer rows, so they're not as useful for this sort of application. So yeah, and it'll train it in terms of, it sets aside part of the data as well as sort of training data and validation data, because there can be an issue when you're training things like surrogate models and neural networks, that if you spend too long training them, they become overfitted. So they'll try and really modify the function so that every single data point sort of fits their curve in the case of 1D, but it's not actually 1D, which then can make them bad at predicting results outside of the parameter space. So it sets aside some sort of untested data that then it also tests. So when you see it, you get two curves, the sort of validation data and the training error that you can have a look at to see that it's not being too overfitted. So in this case, it'll do its training, and you'll get two essentially functions. A function that takes in the inputs you've specified and gives you a temperature, and a function that takes in your inputs and gives you the conversion factor. And this essentially can then replace your finite element model, as long as you're just interested in those two outputs, which might be the key outputs for your case. And there's no limit on the number of input or outputs. So you can see the sort of way that these neural networks are set up. You have a series of input layers, which are your inputs, the sort of coordinates and the material behavior in the case of the tubular reactor. And then they get passed to a series of nodes, which are meant to represent these neurons. They all have different weights and an activation function that they applied to those inputs. And they pass on to another layer and another. And this gives enough complexity that as you train it, it should be able to, should be good at fitting more complex nonlinear behavior. But yeah, it's a bit of an art, and you should really sort of consult neural network sources to try and have a look at the best way to set these things out. So yeah, you do your training. So you have these internal parameters, the weights and the biases, and the sort of algorithm is trying to modify those to best fit the results you've got. And you see, as you start to train, you get these two plots. You get the training loss, which is on the main bulk training data, and then the validation loss. So if you ever start to see the blue line start to go up, that means you've probably started to overtrain it. So, maybe start again. But yeah, so you can run this as long as you want and try and get to a low enough error value that you're happy with. And then you stop it whenever you want, really. And then you have the sort of surrogate model function available. And then you can sort of integrate that into your app. So yeah, training loss reflects the model performance on the primary training data, and the validation loss indicates its performance on the separate subset that it's kept apart for validation. So essentially, I mean, in terms of, giving some intuition for what these, it's just replacing the full finite element model with a lookup table, and then the gaps between the points in the lookup table are filled in by this complicated nonlinear function that you've trained, which is your sort of surrogate model. So instead of solving for the model, it just evaluates this function. Okay, so the example we're going to have a look at is the tubular reactor that we've seen on the slides a few times. So you can solve this. It's quite a quick model to solve anyway, which is good because you need to run it lots of times to get the training data. But yeah, it takes maybe about 10 seconds to compute. So it's this elementary sort of exothermic reactions. We've got a sort of laminar flow going through a tube, and these concentrations that react to give a separate species C. And we have some sort of cooling behavior. There's a heat. We're solving for the heat transfer because the reactions are giving off heat. And we have a cooling jacket around the tube that should provide some reduction in temperature. So it's an axisymmetric model. We haven't really touched on axisymmetric models that far, but if you have that sort of symmetry in model, it makes it a lot quicker to solve for. You can, instead of solving for the full 3D, you just solve for a 2D slice. And COMSOL will automatically revolve your 2D solutions to give you a full 3D visualization at the end as well. And the results we're interested in are the temperature and conversion rate as a function of these coordinates. So 0 being no conversion and 1 representing full conversion of A into C. And the input parameters we're interested in are the activation energy, the thermal conductivity, and the heat of reaction. So that we get, as I mentioned, so that we get a full 3D, the R and Z also get used as input parameters. So our final two functions that we get, functions of the coordinate, and then these three parameters. Okay, so let's go into COMSOL to talk through most of this stuff. It's probably better. So yeah, this is the full FEM model. You can see it's 2D axis. Simple geometry of just a cylinder. In the we haven't touched upon variables as well, but you can define your own variables. So these is where we've defined things like the flow profile. So we don't explicitly solve for the flow profile here. We just specify it. The sort of conversion rate as well is defined here, and the sort of heat that's produced by a reaction. So this Q becomes our heat production related to the sort of amount of reactions we're having and the heat of those reactions. This will then go into the heat transfer in fluids as a heat source. We have the temperature at the inlet set to T0, and a sort of heat flux, a sort of convective cooling due to the thermal jacket, which is also related to this boundary PD. We won't talk about this too much, but that's sort of meant to represent this sort of circling sort of convection as well that's happening in the cooling jacket, which would be an extra fluid as well. We've then got the outflow, so that's our heat transfer fluids. And then in here, we've got a sort of concentration of species, which will then be carried along by our defined fluid velocity, which is here, a Z component, well, Z flow. And then we have a reaction that's going to occur at this given rate. So when we have the model, which would be working, the first thing you would do is you would enable this and train it. So we sort of went through this already for the slides, but you tell it the outputs of interest. So in this case, it's the temperature and conversion, but because they're being sampled at specific points, instead of using those variables, we have point probes, and you can see the point at which it's evaluated are the input parameters that are getting sort of scanned through in our sparse parametric sweep. So we're sort of sampling the temperature and conversion at random points with random combinations of the other parameters. Well, not random, but somewhat random. So yeah, those are outputs that we get that will be written to the table. And then these are the choices that we're modifying, so the point at which we sample, and then also these different behaviors related to the chemical reactions. And we specify here the number of input points, which will be the number of solutions, well, the rows in the design data table. So this would be the most of the time when creating it. I don't know how long it would actually take to train this, but you're talking at least several hours, I think, in terms of generating the data. Sorry, not training. But the data already exists in this model, so we can disable that. So we can just compute it to compare for a second. If I compute. So you can see it is quite a quick model to begin with, but it's going to shift being pretty quick to basically instantaneous. So there we go. So you can see the sort of results that they're getting from the full 3D, from the full finite element method model. Yeah, I don't know that there. But yeah, here, and then you can see how this sort of compares to the surrogate model. So this is the function that's representing it. So before I mention this, I should probably go. So then up here in definitions, we have the deep neural network. So this is where you define the amount of layers you have and the sort of how many output features that go out of them. So those are the sort of lines coming out from each of the different nodes. Then you tell it what each of these columns represent, and you typically don't modify these too much. But yeah, then you would do some training. So if I can probably continue training and see what it looks like. Oh, there we go. So you can see, because I've continued training, it's not actually getting much better. But you would see if you'd started training with a completely, the neural net, their function is completely untrained, it'd start to drop before it's clearly got to a point where it's sort of leveled out. It's not going to get much more accurate than this. Okay. But yeah, so this is what generates the functions. So these DNN1 and DNN12 are representing the temperature and the conversion factor. So they just take in the arguments and spit out the solution, which is a lot quicker. So you can see this is quite good, especially, I mean, this is a qualitative, so we're just looking at it. If you got into the accuracy of the numerical values, there might be some difference, but you can see from a qualitative aspect, they're pretty much identical. So you can then incorporate these functions into your app. So they've already built an app for this one. So if we go to Application Builder, you can see we have these forms and methods which represent different things that happen when you click buttons. So you can see this sort of layout here. This is where you'd start to modify things and start to drag and drop these and add extra objects. And when you're happy with it, you can then test the application. So this will open up in a second. So you see here what they've included is you get a few windows representing the results you might be interested in, things like the temperature profile and conversion profiles for both surrogate model and full computation here. And you can see now we have these drag and drop for the sort of different behaviors, the things like the activation energy. And these are tied to the surrogate model. So if I mean, it's not very obvious on that one. If I maybe do this one. So this is sort of, it's constantly changing because it's using the surrogate model. So as soon as I drag this, it can sort of just instantly evaluate the new solution. So as much as 14 seconds is pretty quick, it wasn't as quick as this. So it gives a new level of sort of interactivity to it. So you could just slide this as much as you want and see the different results instantly. And then when you've slid it to a new position, you can, if you want, then compute again to get the full computed solution. And then these line graphs compare the two. I think. Might not be there. But yeah, so, and you can see the conversion here. Oh yeah, let's have a look at both together. Oh yeah, so we can see that they're a pretty good agreement even when you get to things like line graphs. There's only a small difference between the two. Okay, so I think that's pretty much everything. So yeah, as I mentioned here, if you have sort of the ability to do parallelization and run on a cluster, then you can speed up the data generation aspect of it quite a lot as well. And then you train on the data, you can see here. And then when you have it, you just effectively have these functions available to evaluate at any point. And we've covered most of this when we were talking through it. And you create the app. So you can add as much as, you could include more output parameters and more sliders here. This is all sort of completely controlled by you when you're designing the app. And the sort of preview options here as well were created during the app's creation. So yeah. So they become updated pretty much instantly. And you can compare the two, this sort of computation time. And you can, I don't think, I must have had sounds turned off, but you can also in your apps start to include things like sounds that play when the simulation runs or emailing the results to some specified address down here. Yeah. Okay, so that's how you can integrate surrogate models with your apps to improve them. We have a few, it is quite a new feature to COMSOL, so they are still sort of developing it. But we have a few examples on the website already. We have that tubular reactor that we went through. We also have a thermal actuator and a battery rate capability application. If you want to have a look at those, either as sort of examples of what you can do with surrogate models, but also the apps. So if you're interested in app design, they'll show you how that sort of aspect of it is done as well. But yeah, so other than that, Similarly, there's lots of stuff about apps on the website and blogs on surrogate models. So if you want to sort of learn any more, you can go to the website and get in touch with us on support. But yeah, are there any questions?
Yeah, but I'm the only one for now. Can you integrate surrogate models back into simulations? So use it as a domain, run it on, like, I don't know, maybe you've got a small thing that deforms and you want to test it in lots of different flow conditions. So you build a surrogate model of something deforming,
Yeah.
and then you put it into a larger flow domain.
Yeah, I can't see a reason why that wouldn't be possible. Yeah, because when they're trained, they're just functions. So you could then use that function as a input to the model, maybe to define a prescribed displacement or something like that.
Okay.
Yeah, so I think that should be possible. Yeah, because we've mainly talked about apps, but there are other use cases. It's also, if you have very complicated material data that maybe depends on more than 3 arguments, then that wouldn't have been possible to represent using an interpolation function. You could use a surrogate model. So it's not just tied to apps. You could start to integrate it as well.
Okay.
But yeah, any more?